Hello, I'm MC Toon, and it is not Tuesday night. It's Thursday night, and I've got something I've been looking forward to for a while. I think it will be a good conversation between myself and, oh my goodness, I got to fix this quick. Myself and, well, you can say hi, KalebFE.
Caleb, what is going
Caleb.
on, guys? Welcome. Thank you. Thank you for
Um,
having me, McToon.
you see, the name Gene Techman is still up there. I got to fix that. Give me a
I am
second.
not Gene.
Give me a second. There it is. I was so Caleb. I'll just write Caleb.
Cool.
There we go.
Works for me. That's my first name. Not
Fixed.
trying to hide it.
Right. Not like Russian vids. I don't think his real first name is Russian.
I'm not familiar with him, so I'm not sure.
Oh no?
I couldn't tell you.
Oh,
No,
he's
no. I'm
he's
I'm more on the
hilarious.
TikTok. I'm more with the TikTok crowd right now. So I'm slowly, as you probably know from my last YouTube video, I'm making my way over into the YouTube crowd. But right now, I'm with the TikTok crowd.
Yeah. All right. Well, I had noticed. So you were on TikTok on a live with
Globe
Globe
man.
Man and some other people, and I thought, hey, this looked like a little different interaction. You'd kind of made some decisions about, like, you're going to interact differently with people, like
Yeah,
more actively, and I'm like, that's awesome. Let's. And you had a good talk with Globe Man.
yeah.
So and if this is YouTube, so Globe Man is a TikTok obvious Glober. He was on here a couple weeks ago. Um,
Yeah.
so that's who Globeman is. That's who I'm talking about. But so the what I set a couple things, and so we kind of have a little bit of a game plan here. But the idea is that the gravity exists, and we know about it, and we can test it.
And
That's
I
the
would
idea.
disagree.
Exactly. So, but you would ask Globeman something really good. So about the forces involved in the Cavendish experiment.
Yep. Do you want me to detail or?
Yeah, ask. I mean, ask me so that the crowd knows what it
Yeah,
is.
sure, sure. So yeah, tonight we wanted to debate bendy space-time or mass attracting mass, Newtonian, Einsteinian gravity. Essentially, my claim is that you can't isolate electrostatics from the apparatus or the atmosphere that encompasses the apparatus. Therefore, you can't just claim that it's gravity. So I would ask, how would you do those things when admittedly you can't use even a Faraday cage to isolate them?
All right, a great question. So for the answer, here is, I'm going to share to you so you see. So I'm sending both things. All right, so you see the book here, right?
Yep.
All right, this is, I have to hold it up because the light there kind of reflects funny, but this is Foundation of Electromagnetic Theory. This is the one of the books that I used when I was at the university studying electrical engineering. I after university, I did not pursue a career in electrical engineering, rather preferring to do software engineering. And but the background is still there. So I'm jumping here right here to page 27, where it's talking about Coulomb's law, and it's a little bit. Let's see if I can get there. You go. Is it upside down? I think it's
No,
upside
no,
down.
no, but it's right side up for me.
It writes it up for you. It's upside down for everybody at home. So let me see if I can
Oh
fix
yeah, yeah.
that.
That's definitely upside down for everybody.
Yep. And nope, that's not it. I need it to be the right way. There it is. I mean, they're gonna want to see it the right way. Transform. There it
Everybody
is.
turn your phones upside down.
There it is. There we go. There it is. Right side up. Okay. So here's Coulomb's law again. Right there. F equals 1 over 4 pi epsilon naught times, that's just called sometimes the Coulomb's constant, times Q1 times Q2 over R squared. And then to the right there, it says R in bold, 1, 2, and then over R, 1, 2. The R in bold in this particular book, things that are in bold are vectors. And the 1, 2 determines the direction, which is just a kind of an arbitrary thing. One, it's from charge 1 to charge 2. So that's the law. I'll put it down, but you know what I'm going to do? I asked my wife, and she looked at this, and she's like, "Could you just write down the words instead of using letters?" I'm like, "Oh, that's a great idea." Because she's not an electrical engineer. So I will write down. And what I'm actually going to do is I'm going to use this. I'm not actually going to. I won't write down the constant, but there's a constant. I'll say it's it's not a. Forget
An
it. I'll write the
approximation.
constant. Charge 1 times charge 2 all over the radius squared. The radius would be the distance between them. This is specifically for point charges. There's slightly different derivations you can do for other things, but it works fine for point charges. So the important part is charge 1 times charge 2 over r squared. The other thing is that the direction of the charge matters. So if you've got two of them that are positive,
Yeah. They're going to repel.
repel. If you got two that are negative, they repel.
They're going to repel. Yeah.
And this is different from gravity, which is always attractive.
Yep.
Plus minus, minus plus are both attractive. So if you just have a random charges between two points, half the time they'll repel and half the time they will attract. So in fact, if you get a point here and a point here, and you can, if they're insulated, if they're not touching a conductor, then half the time they will attract and half the time they'll repel. But if you were to connect them with a wire, so you'll connect the two of them with a wire, an insulating wire, and you don't know the charge, you just know that there is a charge. But as soon as you connect them with the wire, what happens is you short the electrical potential. They're now both going to be at the same potential. And if the net charge before was positive, it'll be positive. If the net charge before was negative, it'll be negative. So let's say it's going to be positive. So you have positive some value here and positive the same value there.
So they're neutral, right?
They're not
if they're connected.
They're not neutral. They're both just at the same electrical potential. They can still have a charge, right? So if you shuffle your feet on the floor and you build up a charge in yourself.
Are we talking specifically about like the lead balls in a Cavendish experiment, just so I'm following?
Yeah, we will, but we're not there yet. I'm
not
just
right now.
The
Okay.
foundations,
Okay.
Yeah.
Cool.
So if they could be the same charge if you have them connected by a wire, but they're not actually touching a conductor that goes to ground.
Yep.
And they're not necessarily touching something else. So somehow electrically isolated from other things. But if you touch them together with the conductor, then they're both at the same charge.
Sure.
And if one was 0 before and the other one was 10, now they're both at 5. Or, it averages out.
Yep.
But what's going to happen?
Electrons will be passed.
What's going to happen? You got a plus charge here, plus charge here. They're going to repel. And
sure.
if also you have, in other circumstance, you have, right?
They're going to repel.
They're going to repel. So
yep.
Minus, if they're not connected to ground, and if there is a charge that's not negligible, they'll repel each other. But now, if you
we're not disagreeing yet.
Okay, I'm glad because it's well established. This goes back, well over 100 years.
Sure.
So then now what you do is you can connect it to ground. And so typically the symbol for ground is like this, right? So you can go and you can connect
and then the charge will leave.
The charge to ground. It will discharge both of them.
Yep.
And you have 0. Both are at 0.
I would disagree though. They're made of atoms, correct?
Yeah, but the net charge is 0. So they're made
Explain
of atoms.
Net charge.
The net charge would be the summation of the positive charges and the negative charges together. So if you have,
so would you say they're neutral then?
Yeah, they're neutral, 0.
Okay,
yeah, they're
cool.
they're at ground. Now. So, and it's a good point, right? So you've got a molecule right here. We've got your plus in the center, and you've got
the electrons surrounding it. Yeah.
There. And so I just drew this. I mean, this is a hydrogen atom, right? But they're in balance here. Now, if you had the case here where we're still at, it's not connected to ground. So you could have an ion there where you've got a net positive charge or a net negative charge where there's too many, where there's a disbalance between the number of protons and the number of neutrons. So this would be right here a negatively charged ion, or what we call an anion.
Wouldn't that be polarization?
No, there's no polarization in this one. When you lose an electron, it's an ion, and the charge is now positive. But if you take a more substantial, right, you get a bunch of positives in there, and normally there's going to be a balance between them, right? And so you've got your cloud of electrons around there. Normally they're the same, but let's say that you get an extra, you get a spare electron, right? Now that's what we could have here, where we have spare electrons, and because they're connected by this wire, they're going to be equally distributed amongst the whole system there.
I'm following.
But then when you connect it to ground, right? If there's too many electrons, they'll go to ground. And if there's not enough electrons, they'll come in from the ground. And so then again, you're at a net charge of 0. They're at neutral. And so then now you're back to having a balance between the number of protons and the number of electrons in each atom.
Sure.
All right. So that's important, that now in one case, if they're connected to each other, they're going to repel if they're not touching ground. Or if they're very close to neutral, they're going to not have any net force on them. But if they're at ground, the electrical potential between them is nothing. The electrostatic potential between them, Coulomb's law says, well, because if one of the charges is 0, and actually both of them are now 0, you've got 0 times 0, which is 0. Your force equals 0. So that's how we know in a well-constructed Cavendish experiment or apparatus that there is no net electrostatic attraction between them. If they were not connected to ground, there could potentially be a repulsive force between them, but even that is actually not very likely. So,
okay.
Questions?
No, I follow everything. I've been studying this last couple of days, so I understand. Yeah, I would agree.
Okay.
But in relation to the Cavendish experiment, what I would say is you cannot remove the electrostatic force from the atmosphere that surrounds the apparatus. So over time, having these balls hanging, the apparatus would be affected by the atmosphere that encompasses it.
How would it affect it, you think?
Well, didn't you just explain right here with the electrons that surround the atoms and stuff like that? It could become polarized, as well as also there's van der Waals forces.
Yeah, van der Waals forces are at very, very short ranges, and so much smaller range than the Cavendish. So it's not van der Waals isn't really a likely thing. But yeah, all right. So if you're in the atmosphere, the thing is though, a well-constructed apparatus will be connected to ground.
Sure.
And it's not hard to connect to ground, right? If you live in a modern house, the third plug is ground. But when they're doing, science, they tend to have, like in a building, they'll have a specific grounding pipe sometimes, or just rod that they actually pound into the ground many feet deep to get a really good ground, and they'll connect it with a good thick conductor.
Sure. I don't see that. Well, I guess in a lot of the experiments that I've seen in like school classrooms and stuff like that, I don't think that the apparatuses are very well set up to isolate from electrostatics, as well as the other forces that could be applied, like the air currents and the different things that could affect the experiment over time as well. That's just my two thoughts.
Fair, but for electrostatics, if it's connected to ground, if the air were to say, well, here, I have some spare electrons, here you go, apparatus, you may have my spare electrons, it'll go to ground and then get equalized immediately at the speed of, electrons traveling Borg Emporia says that the Smithsonian would like to frame my artwork.
What does that mean?
My artwork. Look at my fancy artwork
Oh,
here.
want to frame your
I'm
artwork.
gonna put it in
Okay,
the
your
Smithsonian.
drawings.
So, all right.
So one thing I'd like to say is just when I was researching this, I asked ChatGPT, which just collects the mainstream scientific consensus essentially from online sources.
yeah,
And I said, can you isolate electrostatics from the apparatus of a torsion bar experiment? The answer was, in a torsion bar experiment, the electrostatics of the setup cannot be entirely isolated because the presence of electric charges can induce electrostatic forces on the torsion bar, which can affect the results of the experiment. However, there are steps that can be taken to minimize the impact of electrostatics on the experiment. So it seems like even the mainstream consensus is admitting that you can't completely isolate electrostatics out of the experiment. You can only minimize it. And we both know that the electrostatic potential of electrostatics in general is 10 to the 39th power stronger than gravity is even claimed to be.
it is. But when the charges are zero, the force is zero.
But a lot of people are saying that you can't isolate it entirely. So
you can't. So depending on the precision of your instrumentation, it's going to never be precisely zero, but it might be many. Hold on. Let me get here. Right. It might be there. So yeah, you can't completely. Basically, what you've discovered is that in science, there's no such thing as a perfect measurement. Everything has a margin of error. Yeah. No argument there.
So what I'm saying is, as far as the Cavendish experiment, if you can't completely isolate electrostatics out of the apparatus, I don't think that you can. It's kind of begging the question to invoke that it's gravity if you can't completely isolate electrostatics.
The problem with that is that there is no experiment, no measurement, no nothing ever that can perfectly do anything. And so then you can't actually do anything. You've completely paralyzed our ability to do anything. If your standard is you have to completely 100% isolate everything, that might be a confounding variable. Then I'm saying, counts, right? Because then you can't even use a tape measure. Right?
In what sense? Why?
Because it's not perfect. You can't isolate that the coefficient of heat and expansion hasn't changed the length of the tape measure. I know that the coefficient of heat has changed the length of the tape measure, and that this tape measure, when it was made at the factory, was a slightly different length than it is right now, because the metal in it expanded. Because this room is maybe hotter or colder than the factory was. So the length of the tape measure is different. So I can't use this tape measure by that standard, right?
Wouldn't you agree that that would be like completely negligible?
I agree this would be completely negligible. I also agree that this would be completely negligible.
I would agree if
in a Cavendish experiment, if you connect things to electrical ground, the amount of force that you would get between things that are also connected to electrical ground will be completely negligible. Just like, but this you can get. You can actually measure the thermal expansion on a tape measure.
Sure.
Right. But this, to be able to measure.
Is that the exact number?
Electron. No, I just put a bunch of zeros there.
Do you know
it doesn't even have units. You got to have units. Right? The unit it's a force. What's a unit of force?
I wouldn't know off the top of my head.
You use one every day. Pounds is a unit of force, but it's not the SI unit of force. The SI unit of force is newtons. We never use newtons in regular everyday usage even. You ever think about that? You never did.
No.
Right? If you buy a
because I don't believe in gravity.
Yeah, but force exists. Whether or not you believe in gravity, forces exist, and pounds, right? If somebody asks you how much you weigh, your answer is going to be in pounds, right?
Yeah.
Well, pounds is a force, so there's your uses of force, right?
Sure.
We don't think about it. Pound is a force. It is, and Kilogram is not. If you ask somebody in Europe how much, how much do you weigh? Weight isn't in the answer. They may answer in kilograms, but that's the wrong actual answer. But if somebody says kilograms, that's a mass. That's not a force. It's a different thing. But if they're in England, you know what they're going to give you?
What?
Stones. Stupid. If you ask somebody in England how much they weigh, they're going to give you the answer in stones. Do you know that?
Okay. Nope, I didn't know that.
Which is all right. Now Ruhif.
Can we relate this back to gravity? Maybe.
No, Ruhif is in. You're saying pound is not a force. It's pound force is a force. Hold on a second, Ruhif. I'm gonna have to look that up. Now I might be wrong on that. I'm all right. I could be wrong. Ruhif is pretty good on that. Anyway, this is in newtons, but like the expansion due to heat in this being negligible, depending on the precision you need, the force between objects in a Cavendish experiment due to electrostatics is also negligible.
I would disagree when we're talking and comparing them, and the electrostatic force is 10 to the 39th power stronger. I would disagree. I would say that you're begging the question with gravity itself when they're admitting that it's stronger, but it's not completely isolated. That'd be what I'd say.
I don't think you quite understand what they mean by stronger. But that's fine. That's fine. What
do they mean by stronger?
The amount of force imparted by electrostatics in a torsion bar can be quantified, and in fact has been.
How would you invoke the gravity? How would you measure the gravity?
All right. Well, I'll show for the audience. I'll show the basics of a torsion bar. Right, you got the bar there. This is from above. This is a view from above. Right, so this big dot is drastically out of scale. It's the very thin wire that's holding it up, and then you have something on each side, and because you need it to balance, you need to have the mass of both sides be very similar. Right, so now if I could put the pen here holding it up. Right, this is the wire that holds it up. And then if you're going to measure the electrostatic force, what you do is you put a known charge on that. So you charge up something and you touch it to that, and then you'll have a known charge on it, right? So say you've got a known negative charge, and if they're electrically you don't have to in this example, but if they're electrically connected to each other, if you have a wire, then it'll have the same negative force on there. And then you bring into the vicinity of it. I'll use this, right? You move something with a known force near it, and what's going to happen is it's gonna move towards it, and you can use this with a to measure the electrostatic force. You actually can do it. But
you can't isolate it.
Nothing can be perfectly isolated ever. Nothing. That's never the.
Then I would say it's not a good apparatus to prove gravity.
Well, it's a great apparatus, but the thing is, Caleb, nothing can be perfectly isolated. Never.
Then that's a problem.
Every single measurement you've ever done has been affected in some minute way by lots of billions of other potential factors.
And that's why I'd say something stay theories rather than laws.
No. The difference between a theory and a law, theories don't graduate to be laws. That's important, but that's a different topic. Anyway, you can, if you wonder, well, could it be the electrostatic force? You can test it. You can put a known charge on the Cavendish, on the torsion bar, And then you can bring something near and you say, all right, well, what's our sensitivity to these forces? Okay, now let's go and
But most of the time, the Cavendish experiment is testing it over like days. Like I see these experiments done over days, so it's not like you can just immediately test the electrostatic charge by, hey, is this thing electrostatically charged? Is this going to repel or bring it closer?
But the electrostatic charge doesn't actually change if they're all connected to ground.
Yeah, but everything intrinsically, all matter is electrostatic.
Yeah, neutral when it's connected to ground. You can't forget that. When it's connected to ground, they're electrostatically neutral. And the
but they're
force
still
between them,
electrostatic. So I guess so electrostatically neutral, like there's still polarization to things, especially over time. Like electrons will move around, they float around in the current atomism model.
in metal especially, they flow freely.
Yeah, sure.
So you've got metal here, you've got metal here, you've got metal in the wire, and they're moving around, but their net charge is zero because it's connected to ground. So within the margin of error of your instrumentation there, it's zero. That's the thing. You can actually quantify these things. And so if somebody's like, well, I don't think that a mass detection Cavendish experiment can actually be precise enough because of electrostatics, that can be tested.
So I guess what I would ask is, can I see a Cavendish experiment where the apparatus is as best set up as possible? Because I think we could both agree, if you're just setting up a Cavendish experiment in a room or in a shed, there's many other factors, the humidity of the air currents that could be going through over the time of the period of the apparatus. What is the best apparatus that you've seen for a Cavendish experiment?
Yeah. All right. Well, I'll show it. So yeah, you want to do things like, sometimes they isolate the chamber that the torsion bar is in. Right?
With what? With a vacuum or a
Faraday cage? They'll put it in a chamber, and then they'll evacuate the air. And so then just this small area is in. This is a pretty good way to do it, because the movement of this is what we're looking at, right? So they'll measure the torsion on the wire through. Sometimes they'll put a mirror on it and then a laser will shine on it and that'll magnify the movement. Sometimes they'll actually use like a piezoelectric apparatus to measure the actual twist on it. Sometimes they use the swing, the amount of time it takes to swing. Because if it's in a vacuum chamber here and you cause it to start moving, right? It twists and the torsion wire gets applied some torsion to it, and then it'll pull it back, right? So what'll happen is it'll just go back and forth for a long time, waiting for very small forces. And if you've isolated everything well, it'll just keep going a long, long time. The longer it goes, the better isolated you've got it. So sometimes they'll suspend the bottom of it in oil to actually add some friction. There's different ways to do it, but the actual amount of time that it acts as a pendulum, then the amount of time that the pendulum takes to swing back and forth is what they use. They actually count those swings and they time them, and that tells us the amount of force in the system there. So you isolate that, and then you put in outside the chamber. You bring in, typically these are larger masses, but they don't have to be, and they'll bring it into place, and then it will cause the bar to move this way and this way, right? So this is in a vacuum the whole time, and this is not. That's one way. Another way is to put the entire apparatus in it. There's the one that was done at the University of Washington, put this entire thing on a turntable, because one of the things that's a concern when you're looking at very precise measurements, and this isn't, does gravity exist? This is about how precise can the measurement be? So if you have a large mass over here, the wall of the building or something, and that can affect it, and it can. So they put the entire thing on a turntable, and it moved slowly
Could the Earth's
constantly.
If I am believing in gravity real quick, would the Earth's gravity not affect all of these things?
No, because it's the ingenious part of how it's designed. It's on this bar. And since it's on the bar, right, gravity is vertical here. It's both of these masses are at the same gravitational potential. You know that because you've leveled it. That sometimes they'll put like a little object on near here to balance out, so that the bar balances right. There's other ways to do it, but that's one of the ways to do it. So it isolates the gravity of the Earth. But it's a good point, because some people have said, well, the precision somewhere 5-6 digits deep might be affected by the position of the moon.
Could we look at like an actual video so I can have a reference rather than just drawings?
Sure. All right, let me finish this. So by putting it on a turntable, you isolate that there might be something in the room there. And if you do it over many days, then you isolate you average out the effect that the moon might have on it. But okay, I will let me get back to you and me. I'll set my camera here straight.
And how would you, what about the Cheerios effect? What do you think that could have any?
I prefer Honey Nut Cheerios.
Do you know about the Cheerios effect?
You'll have to explain it to me. I'm not certain if I know.
I can read a little bit of a definition right here. It says objects that float at an interface between a liquid and a gas interact because of interfacial deformation and the effect of gravity, which I think is just a begging the question. But it's essentially just talking about how, like, in mediums like water or in gas, things are just intrinsically attracted to each other. And I would say that and they say gravity, but they don't give any, like, the thing with gravity, you've got to quantify gravity. So currently the model for gravity is Einsteinian gravity, which is bendy space-time. So you've got to be able to quantify that one space and time are physical things that can be bent, as well as whenever we see gravity, we see one fabric where it's bent down. There's no up and down according to the theory of relativity.
Yeah. All right. So let's go to the Cheerios thing. First of all, I think it said that it was at the transition between mediums, right?
Let me see.
Was that like the first
objects that float at the interface between a liquid and a gas interact because of interfacial deformation and the effect of gravity?
So I don't think that would apply, because there is no liquid to gaseous medium here. In fact, is the
atmosphere not a gas?
Yeah, but it's not at the interface between them. The interface between liquid and gas. They're not sitting in liquid.
They're sitting in a gas, though.
Yeah, they're interfacing. But read that first sentence again.
Objects that float at the interface between a liquid and a gas interact because of the interfacial what?
There's no liquid and gas in it.
There's no gas in our atmosphere?
No, there's no interface between liquid and gas.
Explain interface.
The Cheerio effect applies to things that are in the interface between liquid and gas. There isn't an interface between liquid and gas. It's all gas.
So you're saying that this has to be from a transfer from a liquid to a gas for this to be invoked?
No, I'm saying that the Cheerio effect requires an interface between liquid and gas. I mean, that I don't know anything about it. I'm just listening to the words you're saying.
Okay.
And I mean, I don't see how there's no liquid here. So
okay, we can move on. I was just curious what you say to that.
All right. So this is I got a couple pictures of different apparatuses. This is the one. This is the one I was talking about. That is in a on a turntable. Let me get. It's coming up here. So here is the actual device. Like, things inside of a vacuum chamber don't look very interesting because you can't see any. There's this wall between you and the device.
Sure.
All right. Here goes. It's coming up kind of slow, but we'll see in a second. This is from this was done in shortly after 2000, like 2001, 2002. So their video of it is representative of the time. There you go. Let me So this is actually done. This is without the vacuum chamber over it. This entire apparatus is in a vacuum chamber normally. So this is showing the turntable that the whole thing is sitting on. You can see at the top it's got the larger balls on the outside, 4 of them.
Sure.
2 on the top tier, 2 on the bottom tier, and then inside that cylinder in the middle is where they have the torsion wire with the torsion bar with the masses inside.
So we can't see them?
No.
How do we know what's going on then?
It's in a vacuum chamber. Of course you
So
can't
wait,
see it. There's that vacuum chamber annoyingly in the way.
So how do we know that the mass is attracting mass if we can't see the apparatus and what's going on?
Because they're measuring the deflection.
How do we know that their measurements are correct if we can't see the apparatus?
It's a good question.
How would we even know that they're going towards each other if we can't look at them?
Well, because they built the apparatus to measure this specific thing, but it's a good thing if the only way that you will allow it to be valid is if you can see it, then there's certain things that you can't have, right?
Yeah.
You can't have it be.
I would like the experiment to be observable, demonstrable, and repeatable.
Well, this all is.
Those are a different one.
The definition of observation is broader than just with your eyes, though, right?
Well, I'd like to see it with my eyes because what we're trying to see here is mass attracting mass.
Yeah.
So.
All right. So anyway, here's the second one. Again, it's showing that. I mean, it's not all that interesting. This is a complicated
I'd agree.
apparatus that they developed, and it's not flashy, and the movements are subtle. So
I would almost say it proves nothing if I'm being completely honest, because we can't see the mass attracting mass. We just have to believe their measurements are right. And how do we know their measurements are right if we can't see the apparatus?
In science, the beautiful thing, Caleb, is in science, there's the invitation to disprove it by repeating the experiment and finding if they were lying about it or not. Do it yourself at a similar level and expose that they were all lying about it. But it's a
can you
bar.
tell me how you know that their measurements are correct? How do you know?
How do I know?
Yeah, how do you know that their measurements were correct in these experiments?
The same way that I know that other experimentations are correct, that it matches with many other observations, that they meticulously documented what they did, that other people over time in other countries from other places have done the same types of experiments and had the similar types of results. And so in order for them to all be wrong would be that they all had the same exact blunders at the same exact magnitude is a pretty high bar. So that's some of the ways you can do it. You can reproduce this yourself. There have been people that have done their own Cavendish and torsion bar experiments. There's a guy called B.M. Furball that did it in his apartment in Korea. He had a 2-bedroom apartment paid for this as part of his deal there, and he didn't need both of them, so he set up a Cavendish experiment in the spare bedroom. He did the things that you're concerned about. He covered up the vent going into the room. He encased the entire thing inside a plexiglass. He had everything electrically
What is the just so I'm following, what is the plexiglass supposed to do around the apparatus? Is that acting as a Faraday cage, as a ground?
No, the plexiglass was to stop any wind currents. So
okay.
His wasn't sensitive to need a Faraday cage. He wasn't actually he wasn't measuring to 3 or 4 digits the gravitational constant, which you'd need a Faraday cage. You'd want a Faraday cage for that. You'd have to isolate it some other way.
So what I'm hearing is there's problems with some apparatuses, and then to solve some issues, we can't even look at the apparatus anymore, and we just have to believe calculations and measurements. And then with other apparatuses, there's problems with the electrostatics and wind currents and different things. So
there's not. No, I'm saying there's not problems with electrostatics because it was all electrically grounded. And there's not problems with wind currents because he put it in a plexiglass enclosure so that no wind currents could affect it.
But you still have atmospheric electrostatic conditions.
But like I said, it's electrically grounded. Caleb, when things are electrically grounded, there's the sensitivity necessary to actually measure any particular forces due to things that are electrically grounded is ridiculously precise. I don't even know if anybody has ever successfully measured the electrostatic forces between things that are mutually electrically grounded. The amount of force possible in that is so minutely small that it's certainly not something that is going to coincident with the types of things that you would do in a measurement like this. So, all right.
Can I see one of those apparatuses?
Sorry?
Can I see one of those apparatuses that we actually can look at the Cavendish experiment? Maybe the one that you're talking about specifically with that other guy?
With BM Verbal? Yeah.
Yeah, I would like to look at that. Just curious.
All right. And then I don't know, do you know Blue Marble Science?
No, I don't.
So he did a much better one, but in order to isolate the things that you need to isolate, you don't have nearly as much plexiglass. But he did encase the entire thing in a Faraday cage. Everything was electrically grounded, and he specifically drove a rod into the ground to electrically ground things. So,
but there would still be the electrons in the air that could affect the apparatus, in my opinion.
Well, those things can be quantified and measured.
I'd like to see those quantified measurements.
No, this is going to be a quick corrections video to correct a little bit of the math that I got incorrect on the Cavendish results video. All of the measurements I made were correct, other than when I subtracted the 6
I'm just hearing the
millimeters
video. I'm
from
not
side
seeing
A.
it.
I know, and I'm not even on
The original length on side A was 0.703 meters.
This thing is loud.
The error I made is when I subtracted 6 millimeters, I actually subtracted 6 centimeters.
That's
this guy's profile picture.
So the correct number is not
everyone, and a special welcome to all of my
Now there's two videos playing.
A few days ago, with the assistance of
and
the
when you
wonderful
combine that
Marvel
with the
girl,
original
I passed the
calculation,
What is happening right now?
Close the tab. There we go.
There we
Jeez.
go. That's much better.
What in the world?
That was crazy sauce right there.
All right. All right. Let's get him up here again. My computer is, I need to update it. I gotta wait. Gotta make sure I'm not having, can't do it just yet. There we go. Videos. So, and he controlled everything. I love how he did it. He controlled everything through a Raspberry Pi remotely. So he didn't need to go into the room once he set it up.
So how do we know that the electrons in the air around the apparatuses aren't affecting something like polarization?
Well, how would they do that?
Because they would be shifting over time as things are in the air in a medium that is electrostatic. I think it would change the amount of electrons over time in the atoms and things like that in the lead ball.
Well, this is well known. How electrostatics works is well known. So if there's something that might do it, then what is it? I mean, it's not. I
would disagree that electrostatics is well known. Even a lot of people that work with electricity will admit that we don't know what electricity is to the full extent yet. So I would disagree that we know exactly what electrostatics is or what electricity is.
I didn't say exactly. I said it's well known. How these things work is well known. So if you're saying, well, could it be this? Well, what? Well, how would the air impart an imbalanced amount of charge on something that's electrically grounded?
I would just say because it's in a medium that's electrostatic.
but it's electrically grounded.
So can you show that the electrons aren't being affected and that they're not shifting around constantly, creating a fluctuation?
Yeah, because it's electrically grounded. All right,
But you
I'm
can't
having
show
trouble
that,
finding
and
it.
you're good. But I don't think that anybody can show me a video or anything like that proving that this is happening. To be honest, I don't
sounds
really.
like you want to see the actual electrons moving around.
Yeah, I don't.
That's not
so
how electricity works.
So if I'm being completely honest, I don't really even believe in atomism in the first place.
Then all of these questions are a bit of a. You're kind of contradicting yourself, aren't you?
Well, I'm trying to play in the parameters to try to explain this to people, but as well as when you even look into these things, these are just kind of assumptions and begging the question fallacies.
All right, I think I have found. He hurt himself a couple times. He was drilling a hole in lead, and he hit his hand with the drill. He had to get some. I think he got stitches.
Can I ask you one quick question? Just because
Yeah.
I was listening to the last debate, and I don't want this to take us completely off, but did you say that the Michelson-Morley experiment wasn't trying to pick up the orbit around the sun?
Correct. That was not anything that they were looking for.
That is exactly what the Michelson-Morley. Then why was the general theory of relativity created?
A separate thing, the general theory of relativity, you can't ask a question about that in relation to the Michelson-Morley goals, because that was years later. So what were the intentions of the Michelson-Morley experiment? Well, they wrote it down in the actual publication, and they did not say we were testing to see if the Earth was going around the sun.
Were they detecting motion? Were they trying to detect motion, would you say?
No, they were trying to detect the effects of the luminiferous ether on the propagation speed of light.
No,
and they're very clear about that. Even in the title of the paper, they talk. It
says
about
motions through the ether.
Yeah,
and there's tons of quotes from physicists saying that even the special theory of relativity explains that they didn't pick up the orbit around the sun, and they explained it through length contraction. Would you agree or disagree?
Yeah, what they discovered is that since you can't, this was the conclusion that people came to, was that because you can't measure linear speed in space, because linear speed is relative, and that's why the theory of relativity is called the theory of relativity, because things are relative. So
would you agree that it's just a belief that you have?
No, not at all. Okay, so here is, and I don't know if this is the right one or not. I'm scrubbing forward to see. I don't see him moving the test masses. So he has here, darn it. All right, on the fly, you know how hard it is to find things.
Yep. No, I understand. I'm not trying to put you on the spot. I was just curious. I just wanted to look at the apparatus.
I'll just say he did this in his apartment. Anybody could do this. And you can see, though, on the left side there that he has these masses, and the mass, he actually cut off the handle off of a big, I think, 30-pound or...
Yeah, it looks like a dumbbell.
And he used the two of them, and he put them on a bar. And then he controlled that bar with the stepper motor controlled by a Raspberry Pi. And then
Wait, what? What did you say? A stepper motor... run by a strawberry pie?
Raspberry Pi. Sorry. A Raspberry Pi is a computer.
Okay. I'm like, what are we talking about here?
This is a Raspberry Pi.
Okay, cool. I've never heard that before.
Yeah, this is encased in plexiglass, but it's just a little personal computer. This actually has a screen on it. Most don't. That's
pretty sweet.
Yeah, it's got some USB and a Cat 5 there.
How powerful is that thing?
I mean, it's actually the new ones are powerful enough to use as a desktop. They run
wow.
a Linux variant.
That's dope.
This is the power plug. It doesn't take a lot of power.
That's very cool.
Anyway, so that's when I threw out Raspberry Pi the audience doesn't all know that either. So anyway, so use that Raspberry Pi remotely so you can, to control the stepper motor. The stepper motor goes to discrete positions. That's how it works, to move the masses into place. So, but now while I'm in here, let me.
Is grounding just relative to the balancing of the charge with the Earth?
Yeah, and since the Earth is so large, the electrical, the Earth is not, it doesn't have a net positive or negative charge because it's so big, right? You need an ion. Things don't like to be in a state of imbalance, so the entirety of the Earth is so close to electrically neutral that you can, as much as you can say it's perfect, it is, but it's perfect.
So just from what I'm studying, the Earth acts as a negative. From what I've heard from like Richard Feynman's lectures and things like that, they will say that the Earth is literally a negative and the atmosphere is a positive.
No, when you're talking about electrical charge and grounding, the Earth is a neutral.
Interesting. I've never heard that from here, but I'll have to look more into it. Do you have any papers that I can look at that explain that you could send to me that I could read after?
That the Earth is neutrally charged?
Yeah, rather than negative, because all of the physics papers that I've looked into say that it's negative.
I can, dude, this goes back to the mid 1800s. So I don't know that maybe there are.
So do you agree that mainstream science right now is saying that it's a negative?
No. Electrically, the Earth
what
is
if I
neutral.
can show you a paper?
Electrically, the Earth is a neutral charge. So in electrostatics is an imbalance of positive and negative. Right. And okay. So in order to have a positive or negative charge in any one particular atom, it's called an ion, a cation or an anion. You need one too many electrons or one too few electrons or multiple. And then when you put a bunch of them together, then you have a net positive or negative charge. But when you talk about the Earth is very large.
Can I read something real quick?
Sure.
The surface of the Earth is negatively charged due to the ionization at the inner core due to its high temperature and pressure.
All right. And what's the magnitude of that?
It doesn't have a magnitude, but it does say that it's negatively charged.
All right.
So I guess what it'd be is I can show you papers like Richard Feynman and other sources that say that the Earth is negatively charged while you're claiming that the Earth is neutrally charged, but you're saying you can't show me any papers.
Not offhand. I mean, I could send you this book, right?
Can you show me the citations from it?
Foundations
You don't need to send it to me.
Theory. So, not offhand. I don't know what page it's at. Offhand. I know what page Coulomb's law is offhand.
And yeah, I would like that book. I might pick that book up. So if you can send me a picture of the cover, I would love to read it.
I when I was in school, I used it and then I sold it back. But I've recently repurchased the same edition as I had in school. So, all right, I'm gonna show you.
And then ChatGPT would also disagree with you. The Earth is negatively charged. Period.
All right, ChatGPT is not a valid source, actually, right?
How would you explain that?
Ask ChatGPT what shape the Earth is.
Yeah, it's gonna
accept that.
Well, hold on.
Don't be going to ChatGPT.
Hold on here, Mike. So ChatGPT just takes the mainstream consensus of what is currently being purported by scientism. So I'm just saying, I'm not saying that this is proof or anything, but I am saying that the mainstream scientific consensus is completely disagreeing with you that the Earth is neutrally charged. Right. I can't find one that ever says that. So,
all right, I'm. Right, get over here. I'm trying to position the file so I can show you the one that was done by, there we go, Blue Marble Science. So he made his own Cavendish experiment, experiment apparatus measurement. So there you go. There is the overview of it, and you can see on the right, and I'll show you a more detailed one. But on the right, you can see the test mass there, and on the left,
Sure.
it's hidden behind the, it's obscured by it.
I can see it. I like it.
So, all right, here's
I don't think it proves gravity, to be honest.
a little closer up view here. You can see they've got this bar going across, and that bar has a wire. It's really hard to see, but there's actually a wire that goes diagonally and comes down through the bar. That's what's holding up that lead test mass. Right, and then over on the right side, same thing. The test mass, now it's behind this little wall here. And then that wire meets the middle and goes up to the top here that you can't see. It's off camera. So
So the Earth is negatively charged and the ground is trying to get it to match the Earth's. Don't you think that there could be polarization in the negative side of the lead balls?
As I covered, let's go with that for a second. If the Earth is negatively charged, then everything that is touching the Earth would also have a net negative charge, thus repel, not attract. So
well,
if the help your position.
Well, hold on. So it would help the position if negatives go to negative. So if everything is touching the Earth and becomes more intrinsically negatively charged, they would come to each other. Wouldn't you agree?
No, I absolutely disagree, because two things that are negatively charged will repel. We covered that right away.
No, we did. Right. In your drawings, you showed that two negatives go towards each other and two positives go towards each other.
I'll show it again.
Oh wait, no, I am wrong on that. No, I am wrong on that. No. I am wrong on that. I will say no. I remember. No, I am wrong on that.
Okay, good. All right, I'll show you this here. How are we doing on time for you?
But there could be polarization, just fluctuating the electrons if we do believe in electrons, which could. 7:30 here, so 20 minutes.
Okay. So here is you can see here. This is a copper foil. Copper is a really good conductor. So he put the entire thing in this copper encasement, so it's a Faraday cage inside.
Sure.
And everything is then grounded, and you can see a very small hole here, then up at the top again off camera. But the top has a very small hole for balancing atmospheric pressure, so that there isn't an imbalance of pressure as things expand and contract. So again, showing here.
Do we know that all of like the vents are covered up in the room? Do we have like pictures of that for like the air drafts and other things?
You don't need that because the entire structure is sealed, and there's just one small hole at the very top. So
this doesn't look sealed. Can I see it sealed?
Well, no, that's yeah, that's an in progress view there.
Okay. And then, so you're saying go back to the other picture?
Yeah, hold on. I just want to appreciate. I love this joinery here. This is so good. I do some woodworking for a hobby, and look at that precision woodworking. Blue, that's amazing.
I can't lie. I'm not appreciating it near as much as you probably, but it does look like some nice wood.
They're getting wood over this wood, if you know what I mean.
Wow.
All right. All right. There's the overview again. Sorry. Here is, so there is a plexiglass hole here. Not hole, a window. So you can actually see then that there's a mirror inside. This is the laser pointing on it. So when it deflects, you can actually see the laser deflecting off of the mirror. So you get to see the movement that you like. And then at the top here, this up here is where it's there's some adjustments and things there, but it's very small holes to just allow for equalization of air ambient pressure.
Would you agree that air current? Well, I guess air currents wouldn't apply. Temperature changes and vibrations could affect this apparatus.
They could, yeah. So you'd want to, and what they would affect the precision, right? That they would reduce the number of digits of precision in your output. But it wouldn't. You couldn't use. You wouldn't have temperature changes that would somehow cause things to attract when they would otherwise not attract. Temperature changes wouldn't do that. And now when Blue did this,
Did blue control for vibrations and temperature changes?
He did. He did, in fact, he kept the temperature at plus or minus half a degree Celsius. And here is his, and so the consistency of his results is a testament to that. You can see here the blue bar is his results, and the thing is that red is the error bars. So you can see the consistency of his results. He's sitting there at 6.600 E negative 11, right? So 6.63, and it's covered up. I can't see that, the final digit, but I think that's the one to the second one. Series 2 is a 6, Series 3 is a 4 is the final digit. So the Series 1 must be a 5, and then the combined is 0.2. So 6.632 times 10 to the negative 11 is his result there of the combined, and you can see how closely they agree with each other. So when you get results that closely agree with each other, then you know that things like confounding factors are less likely to be the cause of some anomalous measurement.
Sure.
So, all right, I it's gotten very technical. So
yeah, it is. You've given me a lot to research. I'll definitely have to look more into this. I'm trying to understand this as best that I can, but I still kind of have my same rebuttals, I guess, at this point, where I could see that maybe the atoms in the lead balls would be polarizing due to what's going on in the atmosphere and the atmospheric conditions that the apparatus is encased in, that encompasses it, due just being the atmosphere itself. So but you've definitely made better points than other, should I say, dare I say, heliosexuals that have brought this up with me before. You've given me more to look at, and that's really my entire why I wanted to have this conversation, because I knew I would learn something, and I knew that it would further my thought processes in this respect. So yeah.
All right. Well, good. All right. If you have questions, maybe we can do this again and you bring things up. I definitely say I'll give you this. This book is a bit thick. Without having a year and a half of calculus, and I'm way out of practice on calculus. It's tough, but it does. It goes over. It goes over some things like Gauss's law here, which is on page 37 there, and you go. This is beautiful. You're gonna love this. Right there, you're headed. They're solving it for Maxwell's equation here. So you're looking at the curl there. Love the curl.
No, I'd be interested to learn more, and I'm definitely cool.
I think Caleb, the girls love the curl, don't they?
What?
You cut off the curls, but I know that the chicks dig it.
No, my girlfriend actually doesn't really mind that I cut my hair. She kind of got mad at me at the start, but no, it was bothering me too. So it's just annoying. Like I get really hot really easily, so I sweat. So I would get annoyed in certain temperatures of rooms and stuff like that. So it did bother me. But I could, if you're down, I'd love to chat with you for the last 15 minutes or so. To just talk about, if you want to kind of just switch the conversation and talk flat earth a little bit, because I will agree that you know a lot about this stuff, and I do have to study a little bit more to be on the level to maybe more intrinsically talk with you about it in more detail. But if you'd like, we could talk flat earth for the last little bit to entertain the folks.
Sure.
So when you're saying that, I really don't understand how people say that the Michelson-Morley experiment wasn't trying to pick up the orbit around the sun, when even the Michelson-Morley, I have a quote from Michelson, Albert Michelson. One second, let me pull it up, of him saying not that one. Oh, here, I'll read this one. Let me read this one from Richard Wolfson. What happened when the experiment was done in 1887? There was never in any orientation at any time of the year, any shift in the interference pattern. None. No shift, no fringe shift, nothing. What's the implication? Here was an experiment that was done to measure the speed of the Earth's motion through the ether. This was an experiment that was 10 times more sensitive than it needed to be. It could have detected the speeds as low as 2 miles a second instead of the known 2 MPS that the Earth in its orbital motion around the sun. It didn't detect it, What's the conclusion from the Michelson-Morley experiment? The implications that the Earth is not moving. Physicist Richard Wolfson. So when you say that the Michelson,
did you end the quote there, or did it continue?
No, that's just where the quote that I currently have ended. So I don't have the rest of the citation.
If I remember right, and I could be wrong that it's a different one, but there's it continues.
Sure, it might, but
more.
But so, even if it does continue, I think that would be in context where he's admitting that they were trying to pick up the orbital speed around the sun.
Well, I mean, you can actually, I just go to the paper, right? And so the paper's name, the title, and we say Michelson-Morley, but the title is actually On the Relative Motion of the Earth and the Luminiferous Ether.
Well, what about?
So they weren't.
Well, doesn't it say the motion?
Yeah, they weren't trying to measure the motion of the Earth. They were trying to quantify the effects of the motion of the Earth on light, and as light travels through the ether.
Yeah, so they were trying to detect the motion of the Earth with interferometry equipment, and they were trying to pick up a fringe shift that they didn't pick up.
They were determining the effects of luminiferous ether on light. They weren't. Nowhere in here is it like, well, we're trying to measure the motion of the Earth. That was already determined. So it wasn't their goal.
What about the quote?
It wasn't their goal. They were testing light and ether. That was their goal.
No. When we have quotes from Albert Michelson saying this conclusion directly contradicts the explanation which presupposes that the Earth moves, you're saying that they weren't trying to prove that the Earth was moving?
Correct. They were not trying to do that.
So why is Albert Michelson saying this in a quote?
I would need to see the quote there. It's not in the paper. So we can't.
But the literal paper is titled Motion Through the Ether.
Yes. They weren't trying to pick up motion. They weren't trying to determine if there was motion. They were trying to determine the effects of the motion on light.
So would you agree that there's no terrestrial or optical experiments to prove that we're orbiting around the sun and it's just a belief?
No.
So what terrestrial and optical experiments would you invoke to prove that we're moving around the sun?
I would do what Einstein did, and I would reference
Well, Einstein disagrees with you. He says that there's no terrestrial or optical experiments that can prove we're moving around the sun.
I can pull up the actual quote that he said.
Yeah, I'd love to see it.
In his write-up from 1915 or 1916, he says, we refer here. So the question is, how do we know the movement of the Earth around the sun? And he says, quote, we refer to the yearly movement of the apparent position of the fixed stars resulting from the motion of the Earth around the sun. He calls that aberration. And to the influence of the radial components of the relative motion of the fixed stars with respect to the Earth on the color of light reaching us from them, unquote. So there's two things there that he specifically cited as measurements of the rotation of the Earth around the sun. So the first one being parallax, and the second one being the redshift.
So how do you prove that it's parallax of the Earth moving around the sun rather than just the sidereal rotation of a hard shell above us?
Potentially there could be some differences in that. You could make that case, but then you get to the second thing, the other thing, the redshift.
So redshift, blue shift is what you're referencing.
Yeah. So
have you ever looked at
Einstein, right? So you're asking about Einstein and he disagree. No, he doesn't disagree. This is his words. So this was his citation for how we know that the Earth is rotating. Orbiting. Right.
Well, have you read the theory of special relativity?
Have I read it? I've read parts of it, yeah.
So on do you mind if I read you page 62 and 63 real quick?
Of special relativity?
Yep, special theory of relativity.
Okay.
It says, in one of the most notable of these attempts, Michelson devised a method which appears though it must be decisive. Imagine two mirrors so arranged on a rigid body that the reflecting surfaces face each other. A ray of light requires a perfectly definite time t to pass from one mirror to the other and back again. If the whole system be at rest with respect to the ether, it is found by calculation, however, that a slightly different time t is required for the process if the body, together with the mirrors, be moving relatively to the ether. And yet another point, it is shown by calculation that for a given velocity v with reference to the ether, this time t is different. When the body is moving perpendicularly to the planes of the mirrors, meaning if it's moving like perpendicular to the mirrors, you would pick up a fringe shift of the motion of the earth through the sun that's supposedly 66,616 miles an hour. Planes of the mirrors from that resulting when the motion is parallel to these planes. Although the estimated difference between these two times is exceedingly small, Michelson-Morley performed an experiment involving the interference in which the difference should have been clearly detectable, but the experiment gave a negative result. A fact very perplexing to physicists, Lorentz and Fitzgerald rescued the theory from this difficulty by assuming that the motion of the body relative to the ether produces a contraction of the body in the direction of the motion. So they're saying that length contraction, they're saying that the entire apparatus contracted to the point where we just wouldn't be able to tell that the fringe shift between the interferometers wouldn't pick up the orbit around the sun.
Sorry. So I think when you said it was from his paper on special relativity, it was not. That was, to my knowledge, that was from the publication from 1916, which is the same one I quoted earlier.
Sure.
It's not the theory of special relativity, or it's not actually the theory of general relativity. That's a publication he did talking about how he came to get them. Right. Just to be clear. Right. So,
sure. It says the title is Special Theory of Relativity, but you might be right. But either way, it's Einstein.
It's probably, the title is probably Relativity and the Special and General Theory. That's probably the title. I could be wrong.
It's titled Special Theory of Relativity.
All right. It could be. All right. Anyway, but the special theory of relativity is a bunch of math too. But anyway, so it's not actually shortened for the people that are in the lab.
So that's the entire argument, is that the entire apparatus is being contracted. So Michelson, everybody in the room, the interferometry equipment, they're claiming that all of it is being contracted to the point where you can't tell the fringe shift to pick up the orbit around the sun.
That's not actually what Einstein is saying. So I'll quote again from his 1916 publication. Thus, for a coordinate system moving with the Earth, the mirror system of Michelson and Morley is not shortened, but it is shortened for a coordinate system which is at rest relative to the sun. So that's why it's called relativity too, right? It's shortened for somebody else, not shortened for the people in the frame.
I guess I would have to look more into that, because from what I've understand and from all of the Lorentz contraction and the length contraction that I've looked at, they're claiming that the actual apparatus is contracting. Like even videos explaining the Michelson-Morley experiment. Did you make one like Whitsitt, or is this
I
Whitsitt?
totally picked, this is from him. I totally did.
This is from Whitsitt?
I tried to match the same font even, and the colors. I took his colors.
No, but did you make this or did Whitsitt make this?
I made this.
Oh, okay. I love that it matches
100%
like Whitsitt's. That's hilarious.
Lifted everything from him.
That's hilarious. I'm
just
dying.
to have fun. I poke at Whitsitt.
No,
That's what we do.
Whitsitt's the man. Hold on. Just for a coordinate system with the Earth, the mirror system, Michelson-Morley is not shortened. So why is he invoking that in the special theory of relativity here, but then he's saying this in this quote? I don't get that. So he's completely contradicting himself from both quotes, wouldn't you say? Because here he is saying that Lorentz and Fitzgerald rescued the theory from this difficulty by assuming that the motion of the body relative to the ether produces a contraction of the body in the direction of the motion.
Yeah, they rescued it. It's important to keep in mind to understand that what they rescued.
Well, they're rescuing that they didn't pick up the correct fringe shift to prove the motion around the sun.
No, all right. So the Lorentz was he was all about the ether. So Lorentz's salvation of the theory wasn't for relativity. It was to keep the ether. So he proposed his Lorentz contraction, that the ether exists and the motion of the Earth through the ether actually compressed everything. And if you look later, Einstein will talk about he'll talk about that an actual compression like that doesn't have any explanation in electromagnetism, because steel would have to compress the same amount as wood and balsa and foam and feathers and air. That doesn't make sense. So
I'd agree.
That was a problem with the salvation provided by Lorentz and his I forgot the other name. So that's what they're actually saying. But to be clear, and somebody mentioned this is good. Einstein's paper on special relativity is actually called Electrodynamics of Moving Bodies. And I'd forgotten that, and somebody mentioned that it's a good point. So I really do think that what you were reading is the same one as I've been reading. It's from his 1916 publication.
It might be. I don't have the exact source. I only have the screenshots from when I was reading it before, so I would have to pull it back up. But if you'd want, I understand your points there. I think that I don't know if we're really going to get anywhere without looking into it more. Yeah. I would like to talk about, because from the last live stream, with the last couple minutes that we have, the Gene brought up the SR-71 going 2,200 miles an hour. And the actual mainstream scientific claim for why do you know the exact feet or the exact miles in 60 seconds that the SR-71 would have to correct to stay at the same altitude?
Zero altitude to stay at zero altitude change to stay at the same altitude.
How do you make sense of that?
Well, if you want to stay
if it's traveling 2,200 miles an hour and the atmosphere is curving to the convexity of the Earth, how does that make any sense?
Because how much altitude change do you need to do to stay at the same elevation?
Yeah, the same elevation.
Yeah, the same, to keep the same elevation above a globe or a flat Earth or concave. You want to keep the same elevation, so the amount of elevation change is zero.
I would disagree. I would say that would work.
You're asking for the linear drop over that distance, over that time.
Yeah, to stay at the same altitude over a curved surface. Because what I'm invoking is that we're on a level surface that is topographical and that the atmosphere is level compared to the level surface that we're on. So flying at 2,200 miles an hour, I would say that you wouldn't have to correct for any curvature. Obviously, you wouldn't have to make any dip. But on the ball Earth, on the convex Earth, you would have to, because the atmosphere is convexing to the Earth. So the exact numbers that you'd have to dip would be 9.3 miles every 60 seconds and 836 feet a second to stay at the same altitude. And they actually don't even invoke that gravity is doing this, that is the main force that is doing this. They say that it's the atmospheric density, because the atmospheric density causes lift of the plane of the wings. So they're saying that as the plane goes up into
works against the downward acceleration.
But you need lift to fly.
Yeah.
So that's what they're saying. They're actually not invoking that gravity is keeping it at the same altitude over the curved surface. They're saying that the density of the air and how much.
What are they claiming causes it to not continue going off on the same vector as before?
What do you mean by that?
Well,
elaborate.
If on a I'll draw it, because I think it's a good question. It's worth drawing out. And I'll share my screen.
And I really appreciate you being so cool today. Like, I really appreciate that. Even though we disagree, I appreciate you being cool. And I'll definitely be willing to come back since you've been so cool. Yep.
All right. So I'll draw down here. Obviously not to scale. None of this is, but you've got I saw an SR-71 when I toured the USS Alabama in
just in like a hangar.
It's in Alabama. It was outside. I'm like, oh no, that's a shame. Anyway, there's my terrible airplane drawing. Definitely gonna go in the Smithsonian. So there's 4 forces that affect a plane, right? You've got lift, 4 main forces. You got thrust.
Yep.
You've got drag. And then you've got whatever we want to call it.
The downward vector.
Downward acceleration, right? We'll just call it that. So we don't have to bicker, right?
I appreciate that.
Now, if on a flat surface, after you travel 100 meters, the downward acceleration vector is the same. But on a globe.
But wouldn't there be the factor of the lift of the wings from the air?
Yeah, and that. But what way is
wouldn't that overpower the downward vector?
Well, if you give it a bunch of thrust and you pull back on the throttle or pull back on the yoke, but no, what they do, they get to this elevation and then they just hold it, and they balance these four things out so that they're not at they don't want to gain altitude. So if you did want to gain altitude, you give it more thrust, and your lift, when you have more thrust, you get more lift. But then eventually you get to a spot where the amount of lift and the downward acceleration are now in balance again because the air is thinner. And when there's thinner air, there's less lift.
Yeah, so that's what I was saying.
Your new spot where you can stay at elevation. So now
So wait, just so I follow what you're trying to say, are you saying that the airplane is actually not falling 836 feet every second to stay around the convexity of the Earth?
It's not falling. No, it's staying at the same elevation. So
don't you think they would feel that?
Falling is a change in elevation.
So,
right?
So don't you think they would feel 9.3 miles every 60 seconds?
No. I don't think you would. So let me show you this. If you kept on the same vector, right? So this is the same vector. I have two planes. I have a plane that didn't stay in the same vector and a plane that did. So this plane's on the same vector as this one here, but it's gone farther, right? So if they were able to keep on the same vector, well, now its nose is tipped up more in relation to the surface of the Earth down here. And the downward acceleration is actually no longer the same as lift, right? Lift is still up, but the downward acceleration, this is greatly out of scale, but the downward acceleration is now skewed. And all the parts of the plane are it's not a linear rate, it's an acceleration. You're can't play semantics here. You're right, Ruhif. All right. But the downward acceleration has now changed. So because of that, after 1 meter, it's different. After 100 meters, it's different. After 1,000 meters, it's different, right? So it's constantly changing. So you will lose lift because now you're also at higher elevation.
Mm-hmm.
Plus,
due to the pressure
plus some number, right? So you've got your elevation here. So you're at a higher elevation, air is thinner. If you kept on that same vector, right, which you'd have to intentionally do because things will automatically, after you go a little bit, they will automatically shift because the downward vector changed.
Due to the contents of the atmosphere, correct, is what you're saying.
Yeah. Also,
okay.
But it's the atmosphere.
But why didn't you explain this when you were talking with Gene? You just said gravity.
I did. I didn't draw it, but I did. I held up stuff.
I appreciate that you went into more detail with me.
I did this stuff with him, but I got to be honest, Caleb, you're going to grasp this a little more than Gene.
Hey, don't do my boy Gene like that. Come on, McToon.
I've talked to a lot of you guys. And
I've seen you talk to him, yeah.
Gene is, I would say, above standard deviation, above middle. And I'd say you're smarter than that even.
I appreciate that.
On Tuesday, the guy I had was like 5 standard deviations below middle.
I watched. That's why I do what I do. That's why I do this. Do you? How much time do you have? Do you have much more time? Or
I don't have a limit.
Okay. Do you want to jump to something else? I feel like I understand your points with this.
Sure.
I think you understand what I'm trying to get out of this. I don't know how much further and with the limited amount of time that we have. Yeah, there's so many good topics to bring up. So, just so I get this clear, well, I guess I would ask if you do believe that there is an apparatus that terrestrially can invoke the orbit around the sun, what would you use? What would you say?
Well, like Einstein, the parallax, stellar parallax, is a good one.
But wouldn't you? So I'm not like trying to do a gotcha or anything like that. Don't you think that's kind of a begging the question fallacy when it could be explained on the flat Earth model with a dome type structure, sidereally or rotating at 15 degrees per hour?
Don't just toss out fallacies, right? So, is it evidence for something? Is a thing, and so yeah, it's evidence for that. It's evidence for.
But it could be evidence for my side as well. Wouldn't you agree?
Yes, and so it could be evidence for
so
something.
So it proves
else.
Neither model is what I'm trying to get at.
To be clear, you're true if your model has a real good explanation for. I don't think it does, but say it does. It's not a begging the question to come up with something that it matches the model, right? That's predicted by the model. It's just something that matches the model. So
do you mind if I define the begging the question logical fallacy real quick?
Sure.
Begging the question is an informal fallacy in classical rhetoric and logic that occurs when an argument's premise assumes the truth of the conclusion instead of supporting it.
Yeah. So
what I'm saying is neither of us have really good support to say that it proves either model, hence why I wouldn't invoke it to prove that we're orbiting around the sun.
Well, I don't think that's a fallacy, because if you take it to be a super broad thing, then anytime there's any evidence that matches the model, then you would say the same thing, and that's not really how science is done.
Well, I wouldn't say the same thing if there was evidence to support it that's terrestrially invocable.
But there is evidence to support it, though. I don't quite get what you're dismissing. Though.
What evidence would you say other? Well, I know that you're saying that the stars move in a parallax motion, but again, I would just say that proves neither model. So I would ask, what other evidence do you have?
So I do think it's exclusive to the globe.
For what reason?
Well, because we're surrounded by a celestial sphere, these stars can be seen through other than strictly optical means in all directions, all day, every day, and they are not seen in a way that would match flat Earth, because when it's daytime, you can see stars, not see, but you can see stars with non-optical telescopes from the ground. So I'm using C in a very rather.
Is there any not that I'm trying to talk over you or anything, but is there any terrestrial evidence other than looking at the sky?
That's on the Earth.
No, we would agree we're looking from the Earth to the sky, right?
So let's go back to this. This is interesting. Einstein said what about terrestrial? What was his quote?
He doesn't. Here, I can hold on. Let me get it. Let me pull it up. This is going to be my boys Austin's quote, just so I'm sure. Have you seen it? I'm sure you've seen it, right? Okay, let me pull it up real quick. If I can find it. These things on the spot are hard to find.
Yep.
Give me one moment here. So I think I have come to believe something of that nature.
Yep, that's the right part.
Yeah. Where is it though? No way I don't have this ready for you. Okay. While I was thinking of this problem in my student years, I came to know the strange result of Michelson experiment. Soon I came to the conclusion that our idea about the motion of the Earth with respect to the ether is incorrect. If we admit Michelson's null result as a fact, this was the first path which led me to the special theory of relativity. Since then, I have come to believe that the motion of the Earth cannot be detected by any optical experiment, though the Earth is revolving around the sun.
All right, so this is paragraphs after.
Can I read the other one just real quick?
Okay.
To the question whether or not the motion of the Earth in space can be made perceptible in terrestrial experiments, we have already remarked in section V that all attempts of this nature led to a negative result. Before the theory of relativity was put forward, it was difficult to become reconciled to this negative result.
Yeah. So again, we have to keep in mind that this is translated from German, so the specific words we can't get too semantic on when he says terrestrial. But in the same publication is the one where he says, we refer to the yearly movement of the apparent position of the fixed stars resulting from the motion of the Earth around the sun. So when he's talking about no terrestrial or optical things, well, in the same paper, he says that we can use the apparent position of the stars. So
sure,
clearly the apparent position of the stars is not included in the umbrella of these other things that he's talking about, the optical and terrestrial.
Yeah.
So is there a terrestrial a way, and whatever for some definition of terrestrial,
meaning on Earth,
whatever definition he used, he did not find any. So yes, on the Earth, can you measure linear motion? And the answer does appear to be no. And the reason why is because everything is relative. That is, according to relativity, you cannot measure linear speed without referring to some secondary source. So you could look at stars, which requires a secondary source. You could look at the sun. Well, that requires a secondary source. Everything is relative. So we can get our movement relative to the sun, but we can't get our movement relative to nothing.
So I guess this is kind of just going circular. So I guess we could kind of switch it if you want. But yeah. I guess, again, just to make my point again, we would just be looking at the sky and saying and invoking that's why we're moving around the sun, when I would say that there's a dome-like structure above us that is sidereal, rotating at 15 degrees per hour, causing parallax. But if you're cool, we can move to maybe one more topic or two.
I'll say, and somebody mentioned in the chat, a gyroscope measures it, but not actually. And I'm backing you on this, Caleb. Not in isolation. So rotation is absolute. Linear motion is not. So the reason why rotation is absolute is because of centrifugal force. So if you were to accelerate at some very large rate for 10 years, you could. And then if you turned off the acceleration and you didn't look outside of your spaceship to see the positions of stars move, you would not know that you're moving. But if you got in that spaceship and you started rotating and it continued to accelerate the amount of rotation, you would notice it, even if you stopped increasing the amount of rotation, right? You'd be crushed on the outside of it. So rotation is absolute, velocity is not. Anyway.
Okay, I'm following you.
Tony, hold on. Let me say this. So Einstein was, of course, fixed in time. He didn't have access to newer measurements. But PhD Tony, this is a good one. I didn't bring it up because I was sticking with the 1916 knowledge. But PhD Tony says neutrino detectors detect the position of the sun through the day. Its path is inconsistent with a flat Earth. So the direction of the neutrinos that come into neutrino detectors is known, and it comes from below. And they come from the sun, they come from below. So there's a way that we can determine our relative position in relation to the sun.
Okay. I'm not familiar with neutrinos. I would say that there might be, I don't want to throw out the word pseudoscience around neutrinos, but I will look into it and I will further try to understand it. So that's what you would invoke as the best terrestrial, is the neutrinos argument?
That is, no, not the best. I just say that's another one. I don't need to play like I have a list. I don't.
No, you're good. You're good.
Here's the best one. I don't know.
Can I ask you, if you don't mind me switching topics? I'm sure you've seen during my lives where I talk about the seasons. What when you look at the heat map mapped over a globe and it's staying at the equator, and we're supposed to be 93 million miles away in an orbit, and the tilt is the only thing that's causing summer and winter and these different things, why is the heat map congregating at the equator?
That's a great question, and the understanding of it is it's non-trivial.
What do you mean by non-trivial, just so I can follow?
The amount of energy that you get from the sun varies based on your angle to it. And the reason why is because when it's at an angle, there's a larger surface. So if we take a book here that's orthogonal to you.
Sure.
Right. The amount of if you're the sun, and right, the amount of light coming to this is this much. And so if we look on the screen, we can actually draw like a line around it to see how much surface area is receiving light from the sun. But then I tip it, right? And I'm going to make it extreme. I tip it like this, and now you draw a box around it, right? Your box is going to be much smaller.
Sure.
So, but the size of the book didn't change, just that its orientation to you changed so that there's less surface area getting, or the same amount of surface area is getting a smaller amount of light. And that's why the tilt makes a difference. So at the equator, it's always warm because the tilt is always not far from it. It's never tilted far away from the sun. Right? When I'm at 45 degrees north and in December, I'm tilted far away from the sun. Further, the sun is up for a shorter number of hours during the day. Now, at the equator, their sunset and sunrise time varies by a small amount. And living in Minnesota, that's hard for me to get because I haven't experienced it personally. But and I don't know how much it varies, like right on the equator, but it's a tiny amount. So, like in the summer here, how far north are you? What do you know your latitude?
I don't know my latitude. No, okay, I should, but no, I don't.
I'm in Minnesota, so near, I don't know, Washington, Oregon. You're Pacific time, right? So,
yeah,
that's my time zone is going to be right in there. Actually, no, I think I'm about as far north as San Francisco. Could be wrong. Anyway,
I'm a little above that.
So sun sets at like 4:30 in the winter, and in the summer, sun sets at like 9:40. So the amount of time that the sun is up is drastically different too. But at the equator, that doesn't vary. So both the angle doesn't actually vary a lot because it's near the equator, and the sun goes from 0 to 23, and then to 0 to 23. That's it. Where here I'm at 45 on the day of the equinox, and it's even more tilted away in December. So that those two there are a huge part of the reason why it's warmer at the equator. So if you look at the amount of absorbed light radiation, you should have on the globe a warmer at the equator.
Interesting. Okay, I'll look more into it. I guess you'd already kind of know my answers for this since you've watched my live, so I don't feel the need to really go into it. But I would still say, like, the distance of the sun being 93 million miles, I feel like when we look at the heat signature mapped over the Earth, like the North Pole should be extremely hot when it's completely tilted towards it and facing it if we're invoking that type of a situation. But I don't care to really get into the semantics. I just wanted to hear your answer. Do you care if we go into something else, or do you want to stay on that?
Yeah, let's do one more thing.
Cool.
I've got a bunch of super chats. I'm gonna have to read here. I love interacting.
Yeah,
with
sure.
The crowd.
Yeah, I've got to dip out soon here. My girlfriend's gonna be back. So if two questions, I guess this is kind of two questions in one. Why do you think that they would name Polaris, that with the etymology of it meaning pole star? kind of getting at the fact that maybe it will always be the pole star, as well as if there is parallax to all stars. If we're supposed to believe we're tilted at 23.4 degrees on a 90-degree axis, orbiting around the sun at 66,600 miles an hour on average, chasing the sun 500,000 miles an hour, 4.4 billion miles a year through space. How does Polaris stay in the same spot?
Do I have? All right. I don't have a globe handy.
Wait, why do you react like that? Why do you say, come on? Why are you reacting like that?
Because I've heard that. Or look, you're not the first one to say that series.
Of course not. Yeah. Well, I'm just explaining the model. I'm just trying to explain and processing as well. We're processing too. Yeah.
So the precession of the equinoxes is a multi-thousand-year cycle. So, why was it called? You asked a bunch of questions. Why is it called Polaris? Well, when it was named, it was near the pole, so it was called Polaris. But people 2,000 years ago would not have called it Polaris because it wasn't near the pole. In 1572, Tycho Brahe measured it to be 86 degrees 53 minutes away from the center. So it was over 3 degrees from the center. And he calls it Polo Zodiaci Proximata, and I'm totally screwing up the pronunciation. So it's Proxima. It's close to the pole. So it was at the time even, it was the closest brightish star to the center. There's many stars closer at the time and many stars closer right now to the center, but they're not as bright. So that's why it was called, because we speak English and it's our Western, modern kind of stuff that named it that. But I would suggest, I don't know offhand, what did the Egyptians from 2,000 years ago call it? Probably not Polaris.
Okay, that's it. Yep, I've never heard anybody say that. That's interesting.
So how, let's see, how is it that it stays somewhat consistent even though we're moving at great speed? So because the distances are so great, so we can actually measure parallax of stars. Not all of them. Some are far enough away that they don't actually parallax. So they talk about like the distant stars when they talk about parallax. So they index them based on the stars that are so far that there isn't any parallax. So I don't know how that would work in a dome, because some stars have parallax, some do not, some have proper motion, some do not. And the amount of proper motion varies for all of the stars that have proper motion. So how does that all work in a dome? Are they somehow moving around and wiggling around on it? I guess what is proper motion? I guess I should ask that. What do you mean by proper motion? Whenever I mention that Polaris moves, and I just use the words Polaris moves, and I bring up that Tycho Brahe measured it at this particular location, they're like, well, that's not proper motion. And who is they? They is astronomers. So like Danny Faulkner. Danny Faulkner works at Answers in Genesis, who Ken Ham is the founder of that. They own the Ark encounter in Kentucky. So an astronomer works for that organization. He taught astronomy at a university. Also, if I can just interrupt you real quick, could you get me the measurements of Tycho Brahe? Because I love Tycho Brahe's work, and I would be interested to look at his degrees versus degrees now. It's just to compare, just so I'm keeping myself updated. I'll send. It's mc2.net/Polaris. I have. Okay, cool. If you've got it on your website, I'll check it out. So Danny has messaged me after. He's like, you should talk about proper motion. I'm like, okay, I know there is such a thing as proper motion. Can you give me? She never wants to be on camera. Hold on. Your hand wasn't on camera. All right. Thank you. Good night, dude. And thanks for your time. Thanks for staying here for so long. I really appreciate it. All right. So what was I saying? All right. Proper motion is what is proper motion? All right. So parallax. There's There's parallax, there's proper motion, there's precession. Okay. I'm not super up on astronomy, and I hate astrology. Wait a second. Are you in astrology? I don't want to offend you too much, but astrology is dumb.
I don't believe in astrology and the fact that it's like a settled science or anything. Me personally, I do believe that there is influences from the sky though down to the earth in a very special way. So
definitely not science.
Yeah. No,
in fact,
I agree.
Astrology is the how do we separate science from not science? And so Karl Popper talks about astrology in here as here's how we can delineate or demarcate between science and not science. Anyway,
no, I would agree that it's just like a kind of I would believe it's a belief system of mine. I do believe that there is something. I don't think I can prove
it's metaphysical.
At best. Yeah. No, I would 100% agree. That's why I don't say that it's 100% true that people act a certain way because of the constellation and the sun that it was in when they were born. So no, I don't.
Okay, so the precession of the equinoxes is why Polaris appears to move primarily, and that's because the Earth has a multi-thousand year precession, like a top on a table that's wobbling, right?
Yep.
So the wobble of the Earth, there's actually multiple wobbles. The primary wobble is the precession. It's multiple thousands of years long. There is a Chandler wobble and an annual wobble. They're on the order of a few meters. So that is Polaris primarily. Proper motion would be something like Barnard's star, where it moves drastically and you can actually see it like over 2-3 years. You can see it as if you were to time it out. It's like a streak, right? So yeah, PhD Tony comes in right as I'm saying it. Barnard star is textbook example of proper motion. So Barnard star moves quickly. So but the reason why, if all of these motions are happening at the same time, why is it that Polaris and other stars don't move much? They do move, but not much. And that's because they're very far away and they're generally moving with us too. So the stars that we see with our eyes, for the most part, are in our galaxy and close to us somewhat. And they're generally moving with us, right? So they're kind of going around the Milky Way with us. Think about this. If you're on a freeway and traffic isn't inconsistent, you're next to another car and you look out the window, you can wave at them for a while, right? That's the idea, right? And you might have on a freeway, 1,000 cars all in 3 lanes that are all moving kind of the same speed with each other. So that's the idea. There's slight shifts in speed between them. So
I guess what I would have a lot of follow-up questions with that, just like how do we know the distance of stars? How do we know that they're correct? When they've admitted in 2010 in a paper that they were off by 100 light years with Polaris, and they used Polaris to figure the distance of other stars and different things like that. So
and I had a guy, I think it's on my Toon Show channel, who had he's pretty good about Polaris, and so I brought him on, and he's an astronomer, and he talked about Polaris, and so I could send you. I'll send you that because I asked him all those questions because I'm like, I know in general how the distance to stars is measured. And I'm like, well, how specifically did we measure the distance to Polaris?
Wouldn't they just use spectroscopy? Wouldn't that be the answer? Don't they just invoke spectroscopy? I don't know of any other thing that they'd invoke to figure the distance to stars.
No, there's a few things. So spectroscopy can measure the redshift. And that gives a relative distance. Another is different types of stars have different brightnesses, and it's about the actual, like the physical makeup of the star and the size of the star. And so there's a range of, all right, well, this star is this particular color and has this particular spectrum. And so its brightness is this. And because it's, how much light it's outputting at the star, right? But when it gets to us, it has a certain brightness. And so we know it drops off with the square of the distance, right? It's the inverse square law. So we can do the math on that and say, all right, well, we apply the inverse square law to how bright it is, and we know how much light we're getting, and we know how bright it must be because it's this type of star, so its output must be within the certain range. So that gives us a rough range. And of course, these measurements are the error is percentages, but when you actually look at it in the number of miles, it's massive, right? It's a huge number of kilometers or light years of distance difference. The other is parallax, and there's probably others. Danny, send me a message so I can get it right next time. The parallax is another way, because again, like I said, there are stars that do not move with parallax, and there are stars that do move. And so that amount, I'll just finish this. The amount of parallax, because we know how wide our orbit is, the amount of parallax tells us how far away it is. All right, go ahead.
So I'm not denying that there's parallax. Obviously, you've already heard my explanation of why I think on our model that there is parallax. I would deny redshift, blue shift, though. I don't think that that's happening at all. I don't think that that's provable. Because if there were redshift or blue shift to the stars, don't you think that the constellations should be expanding or contracting in a certain way?
Well, they do shift. The positions of the constellations do shift over
Yeah,
time.
they shift in a sidereal rotation. Yes, I'm not disagreeing that they do shift in sidereal
relation to
motion.
each other, they actually slightly shift.
Can I get a measurement for that? I would love to see measurements.
Again, that's on handy. It's on mctune.net/Polaris. I have
mctune.net
/Polaris. Yeah. So I have a nautical almanac from 2017. And when I made this page, that was the newest. Actually, no, I would have made this in 2018. And I have a nautical almanac from 1900 and from 1850.
On here, just so I'm following, these just look like calculations. Is there any observations showing that these have contracted? Or because when I look at star maps from like Egypt or these different constellations, they're mapped almost essentially at the same size from what I understand.
So yeah, all right. So when they publish a nautical almanac, they publish it for the year ahead. Right. So yes, it is a calculation based on historical movement. But it's accurate. And if it weren't accurate, they would find out why and they'd fix it for the next publication so that it would not be inaccurate, because they want to be very accurate with it. So
cool. I'll look into it.
Yeah, these the positions vary with the other thing is, a lot of people miss this. The precision of this particular of these measurements is in the arc seconds.
I've been studying arc seconds, arc minutes. Arc seconds is very, very, very
precise.
It's
1/3600th of a degree.
Yep, of a degree. And
so
of a circle.
they're precise to better than that in the positions of stars. So
okay, very cool, very cool. I'll look into it. I definitely want to study this more. And again, just like with Globe Man, if anybody can be cordial with me and have these debates, I'm willing to come back. I'm willing to talk more. And you've been more than extremely cordial. So I really appreciate this conversation. I don't know if you need to go. I probably do need to go. My girlfriend's going to roll up here. So I appreciate you being cordial.
Right.
I appreciate you.
Yeah. Bob, the science guy, he's like, he wants to talk to you anyway. I'll connect you with him afterwards.
Can you connect me to Simon Dan? I'm trying to get a debate with Simon Dan, man. He says he won't debate me because it's a fact that the Earth's a globe, man. Well, how lame is he? He doesn't. He doesn't want to destroy me, quote unquote, destroy me. Tell him to debate Caleb. Tell him get into a room with him.
He offered not on this topic, but he did offer to debate somebody. But he's like, well, you need to complete a test first.
Oh man.
And it would be a test
with the semantics. See, you're a cool guy, McToon. You just show up. You say you actually reach out to me. You say, let's have a chat. Simon Dan literally said in the live stream today that he won't do it. What the heck is wrong with that guy? Yeah.
He does live streams. Wait, what live stream was Simon Dan in?
No, it was a TikTok debate on Maria's live, the one that you watched me on. They were talking. Globe Man was like 1v3, talking to a bunch of flat earthers, and then Simon Dan popped up in the chat, and I added him.
Oh,
yeah, I was just talking to him in the chat. He was just chatting in the chat, but he said he wouldn't debate me, which I think is lame, man. I feel like that'd be good for his audience, be good for my audience. It would be fun, but no, I've seriously enjoyed this conversation. I really appreciate you giving me so much time, and you've given me a lot to think about the Cavendish experiments and more to study, and that's all that I'm seeking is knowledge. So it's been cool. So I appreciate it, man.
All right. Well, Caleb, thanks for coming on.
Yeah, no problem.
Everybody else, feel free to stick around as Caleb sees his way out. We'll hook you up with Bob the Science Guy sometime.
Okay, later, guys.
All right. Okay, well, Caleb has left the build. That was nice. That was, you see, I was tried to do with Caleb a little something different. So let me wrap up. I'll close the Zoom meeting here. And then I got some super chats to read. People, you've been super, super kind. Thank you so much for that. I knew I wouldn't be able to read them to him. I wasn't this, right? And I gotta be honest, sometimes people, sometimes you're a little mean. I don't blame you, but sometimes you're a little mean. So, oh my goodness. I always have, in the middle of a debate, I know what's going on by how many direct messages I have afterwards. And so looking at Discord, I'm like, oh, Ruhif, PhD, Professor Phil Bell, Mandelbrot set. Thank you. I'll unless you think it's something I need to read right now, I'll get back to you afterwards. I love it. I love seeing those afterwards, and sometimes I'm like, dang it, yeah, I missed that. In the middle of it, I sometimes miss it. So anyway, let's see here. I'm gonna jump ahead to Many Karen says we've never seen Mrs. Toon, therefore she doesn't exist. Flurf logic rules. Yeah, that's totally it. And well, you did see her. Give me a fist bump. She did. I don't know what it might take. Probably she will never. He's like, I can't believe you talked to them. They're just wrong. So, she's like, she has no time for it. She's funny. The Big Man 389 says for $2, Caleb, did you and Derek find the moon yet? Caleb was not looking for the moon. It was just Derek. I love that. So Derek is his Caleb's buddy on TikTok, and they do a podcast. You got to pay to watch their podcast. I can't imagine it. Anyway, no, Derek has not found the moon yet. And if you're wondering what that is, go to my Conspiracy Tunes channel and find the video on Professor Ick. PhD Tony says, your guest is wrong. Rarely do I need to go past that when I have a flirt on. In gravity observations, we guarantee the electrostatic force is vastly smaller than the signal we are trying to obtain. Yeah, and I tried to make that clear. But he just kept kind of quoting Witzit's thing. Well, electrostatics is 10 to the 39 more powerful, or whatever the number is. Without really understanding that there are implications to it, as covered in here. So, can you imagine? Can you imagine him reading that? Weatherhelm says, ask the kid what his level of education is. Betting he has never passed college physics. To my knowledge, it's probably high school. I don't want to say more. My guess is that he probably did not go to college, but he may have some. Delco says, I see he's a Whitsitt and Ken Wheeler fan. Yeah, so if you're a Whitsitt fan, you are by default a Ken Wheeler fan because a good quantity of Whitsitt's cherry pick quotes, or not even cherry pick, are from Ken Wheeler. And of course, Ken Wheeler is a pseudoscientist, nonsense peddler on YouTube. I forget the name of his channel. Don't say it. It doesn't matter. Nobody should go to it. But he makes up crap. He just says things about gravity, electromagnetism, photons, electrons. He makes these claims about what they actually are, and of course none of what he has is empirically supported, and really none of the things that he claims could be empirically tested. And if you can't test it, it's not science. If it's pretending to be science, there's a name for it. So, oh dear, real sickness. No doubt he might actually possess a GED thanks to our no left behind policies. All right, let's not be too mean. So, all right, there's a spectrum of people that I've had on here, right? And to be honest, right, that there's people on either side of the peak, and there's people to either, there are multiple standard deviations, smarter or less smart than the peak for flat earthers, and so put them where where you think they are. Oh, I should mention it now. I see that Siggy Sigwald gave 50 memberships. Thank you again, Siggy. You are absolutely too kind. And I will definitely update the scroll going along the bottom with the new recipients before next Tuesday. So PhD Tony says, is your guest aware that there are hundreds of reproducible, peer-reviewed, highly precise gravity experiments other than Cavendish? He knows that there are more. And because he thinks that because electrostatics can't be perfectly accounted for, then it doesn't matter. And so somehow it is coincidental that when you introduce the test masses, that they move into place, that the torsion bar twists coincidentally. If they, like I covered, if they had the same charge, they would repel. They're electrically connected to each other at the same electrical potential. They can't have a significant difference. So, but when you've never covered these things, everything's a black box. So I think Stringer News 1 says cite Cole's law or coleslaw. I do not. All right. I don't like cabbage. I don't like coleslaw even more. And I really don't like the variations of rotted cabbage like kimchi or sauerkraut. Please no. Oh, geez. I can't believe people are like, oh, this needs to be thrown out. Let's eat it. No, let's not. Let's not. PT Tony says, we observe curvature of space-time in the form of gravitational time dilation. Your guest's skepticism on this topic is based in complete ignorance. Indeed it is. So Caleb, time dilation does exist. It's on my website, mc2.net/relativity. I have a handful of the groundbreaking experiments of each particular type. So it's got Aries, Fowler, Michelson, Morley. It's got the first measurement using the Sagnac effect. One of the first, I don't know, the first big one. Michelson, Gale Pearson. I've got one of the the first-ish measurement of the time dilation in the Havel-Keating experiment. So look at that one. Serena's 1 asks, is coleslaw a salad? Bob the Science Guy, if they send you kimchi, you can send it to me. Oh no, Marianne Night Owl says, I love sauerkraut. MC Toon saves more for me. Yes. I've actually, I'm so much opposed to it that I basically won't even try. But one time I was in that Swiss German town in Georgia. I don't know the name of it, but people would, maybe it's Helen, Georgia. And we went to eat at a restaurant. Of course, they're all German restaurants. And I had a Reuben. It's the one time I had a Reuben. And they're like, it's not that sauerkrauty. We fly it in from a plane from Germany. It's pretty fresh. I tried it. It was acceptable a bit. I took it off for the second half. Anyway, PhD Tony said that. Thank you for that. Lael, $10. Thank you, Lael. Says, if you have the Cavendish in a vacuum at 10 to the negative 8, with the strength of electrostatics being 10 to the 37, the strength of gravity, what would the charge of electrostatics be? That's a really good way of putting it. Because none of these people that are like electrostatics, blah, blah, more powerful, they don't actually know how to apply electrostatics. That's the thing. If it's neutral, it's zero force. So, Many Karen for 15 shekels. Caleb can't see charge. How does he know it's there? Yeah, and he did get into the kind of the unicorn hunting. So unicorn hunting is, and he wasn't quite doing it, he was just the ever narrowing standard of evidence demanded for globe evidence, where flat earth evidence is wide open. Anything at all. Like, oh, it could be movement in the firmament. Okay, where's the super narrow standard of evidence that you apply there? So, PG Tony says, in superconducting gravimeters and cold atom gravimeters, we freeze all the air out of the instrument. Electrostatic forces become impossible. Yeah, and on my website, mctune.net/G, I have at least one measurement of the gravitational constant. This isn't even, I mean, there's no question about gravity existing. These are super precise measurements of the gravitational constant. They do have it in a vacuum, in a super cold position. I think this one was in the bottom of a former missile silo to be away from things on the surface, to isolate it. So, man, PhD Tony comes in again with, so your guest has no formal training and thinks that everyone who does have formal training is stupider and more ignorant than he is. Or in on it. They would have to be. You see, he wanted to see the Cavendish experiment, the torsion bar twist. And if he didn't see it twist, then how does he know that it was twisting? Well, the experimenters built it so that they could measure the amount of twist. And they confirmed the things that they needed. And they then ran the experiment and they output a specific value for the gravitational constant. Now, in order for them to output a very specific value for the gravitational constant, which is not in perfect agreement with everybody else's specific value, and for them to be faking it, they would have to be lying about it. And the other people that did it would have to be lying about it. And all of them would have to all communally be in on the lie, to all in different places of the world, different times, different countries, different political situations, output the same number. They're all in on it. There's no other option, right? So how many thousands of people have to be in on it? Now that's a big group of people. And I got to be honest, if you can't keep a BJ secret when there's only 2 people involved, or you can't keep breaking into at night into somebody else's campaign headquarters when there's only 8 people involved, how can you keep all of these other people involved? Somebody who would have had to fake the experiment at the University of Washington and is still employed there, right? He has to be in on it. That's huge. Yeah. How? If you want to test science, but here's in the end, it doesn't matter. If you want to test science, if you want to falsify something, the door's open. Go do it. Incredulity isn't a falsification. Go do the test. Build your own. Isolate all the things that you think need to be isolated to the degree that you demand that they be isolated and show that they're lying, or show that they made an error, or show that it's electrostatic forces at play, isolate them to your satisfaction. If you can't, then incredulity is nothing, and we'll just, I mean, Whitsitt himself brings that up in as a fallacy in debates. So PhD Tony says reading physics papers is kind of futile if you're not qualified to understand them, Caleb. Yes. And it's not even that he's reading them. It's not even that Whitsitt is reading them, because he got them from Whitsitt. He's quoting Whitsitt's cherry picking from not the special relativity paper. And to my knowledge, the 1916 one isn't the actual publication of general relativity. I could be wrong on that. I'll withhold that statement. Please, gotta read it more. Make sure I'm saying that correctly. All right, Leslie Rohrer says he's correct. The charge of the Earth is about 1/2 million coulombs. A simple voltmeter will measure any significant amount of charge. All right, all right, now I have a voltmeter. I have a multimeter. When I turn it on, I get 0. I don't quite know what that is, but it doesn't help his position either. Because if you ground something, and those two objects now have that negative charge, they're going to repel, not attract. And it's 10 to the 39 powers more powerful, whatever that means. So, all right. Well, I would, if I'm wrong on the charge of the Earth, then let's see it. The Sun Express says strong woodworking pornography. Yes. And I haven't said it before on stream enough. The woodworking in that is spectacular. I can barely get pine to not be an absolute shambles. String News 1, remember that voltage is relative to two places. Yes, it is. It is relative. Yeah, so the voltage of the Earth is 0 in relation to the voltage of the Earth. But charge is absolute. Right? Lael says, check your got to lie to flurf. That comes straight from ChatGPT. Hashtag got to lie to flurf, says Lael. What? What are you talking about? You're talking about... I don't know what you're talking about. The hashtag got a lot of flurf. That comes straight from ChatGPT. I don't know what that means by that, Lael. Oh, there it is. Okay. This is clarification. Lewin Cuffworthen says, charge of the Earth. The Earth is neutral. The crust is negative. The core is positive. There you go. Okay, that makes more sense there. So, all right. Siggy Sigwald for $50. Says MC Toon, the most polite rapper of all. Some people butt heads and some people don't. Caleb and I did not. Whitsitt was on here, we would. But I think Whitsitt butts heads with everybody he disagrees with. That's him. So Siggy Sigwald says, haha, he got caught cherry picking. Yeah, I mean that's what, because he's quoting Einstein things that he got from Whitsitt. So Whitsitt doesn't understand Einstein, and so he's quoting Whitsitt's misunderstanding of Einstein. So yeah, and so I think that was about somebody's. Yeah, that was the guy. I forgot the guy's name that was talking about the Michelson-Morley experiment. They're like, well, if the ether exists and the results of Michelson-Morley are thus, if the ether exists, then that necessitates that the Earth is stationary, but we know that's not true. And I think that's the part that he missed. And so, therefore, one of the other premises must be incorrect. The ether existing. The Discord channel. So, yes, I have a Discord channel. Let me look at it quick. Called Gotta Light a Flurf. I thought that might be what he was talking about. I'll peek at it quick here. I'm not going to probably put it on screen. We'll see. Maybe I won't. I don't want to say it too quick. Jump to the bottom. I haven't been in there for a while. Oh, it's a big long thing. All right, can you provide peer-reviewed papers that talk about the Earth being negatively charged? I'm sorry, but I cannot provide peer-reviewed papers that suggest the Earth is negatively charged because such a proposition is not supported by the scientific consensus. All right. So yeah, the Earth is a whole, but then people are talking the crust versus the core. That's different. Yeah, okay. All right. I will definitely brush up on that. All right, jump back to your Discord. Got to scroll back to, there it is. I use Discord sometimes to identify where I am in Super Chats. That's what I'm doing today. There we go. The Sun Express says most ignored words by Flurfs. Through the luminiferous ether. Yeah, and they love to say that they were trying to measure Earth's speed. There was no question about the Earth's speed. And as Einstein mentioned, there are reasons why we know that the Earth is moving. And so it's funny when he's like, that's a begging the question. Well, it was from Einstein, the guy you're trying to quote. Fa of the Q-tube family, QT-oob family, says, if electrons aren't a thing, how would you explain all the electronic devices you're using to be in this live stream? And that is a definite problem. They always talk about that, but I'm like, all right, well then explain, quantum tunneling, explain the very existence of the computer you're using to deny that electrons exist. Oh, it's something else. What is it? Where's the empirical confirmation of it to explain all of these things that we completely rely on for you to say these derpy things? Thinky Sigwald says, I know relativity is hard, but some concepts are not that difficult to grasp. If I can sort of kind of get it, I see no reason why these people can't. It's about the standard deviations above and below some amount of intelligence. Yeah. Shmoku says weather can locally change the charge of the ground. It can, which is a problem for them because Whitsitt and then all of his acolytes claim that the direction of the downward acceleration is due to electrostatics and I think the adiabatic electrostatic charge of the Earth, where it's 100 volts per meter. But of course, near in the vicinity of an electrical storm, this charge reverses and it's significantly stronger. So if the direction of the downward acceleration was due to electrostatics, then in the vicinity of a storm, you should get slammed up to the ceiling. But we don't. And Whitsitt quotes Feynman. In this paper by Feynman, just not all that many paragraphs away from where he's talking about it, Feynman talks about the electrostatic reversal of a storm and the standard, generally there 100 volts per meter of the Earth, and that by superposition you put them together and the drastic charge induced by the storm is there, and the existing 100 volts per meter is small. And Witset's answer to that is, I don't believe in superposition. That's it. So he's citing Feynman. Feynman's talking about superpositions on the specific topic you're talking about, and your refutation is, I don't believe in it. Bob the Science Guy, you are arguing relativity with people that don't grasp basic Newtonian motion or what a Newton is. And we did discover he didn't know what a Newton was, right? When I wrote this, he couldn't name one unit of force. So, anyway. String News 1 says, I gotta go invoke a Riley. We had a good Riley. Siggy Sigwald again says, who are this they people that keep saying things that aren't true? Yes. When there's a lot of black boxes, and a black box is something where magic happens, right? Where things that you don't understand happens. So yeah, there's almost anytime there's math, it's a black box. They're like, well, I don't understand how it happened, but somebody definitely faked it in the math part of it. Well, the they is a black box too. The black box of they can do whatever you want them to do if you're a conspiracy theorist. It answers everything. It's the get out of jail card. It's the God of the gaps. It's the absolute everything. They did it. Why did this person who totally discovered that you could power your car with water, how come he died at the age of 97 years old? They killed him. Seriously. Why the flurfs are always into the free energy crap too. Like, oh, all of these cars that can run on free energy, why did none of them work? Did you make up all the zeros? Yes. He's like, is that the exact number? Yeah, no, it wasn't. String News 1 says, witless, top left, the evidence speaks for itself. Yeah. Unfortunately, all right, so we've had to move back the voting video premieres. I have all of them except for the Austin Whitsitt one that Craig is working on. Now, Craig he's visiting his dad right now, so he can't even work on the video at the moment. So I'm like, don't worry about it. Take care of your family. When the voting videos come out, there actually is no HR department at NASA that's telling us what to do. We'll put them out whenever we do. We'll give it sufficient time for people to vote on them so that we can enjoy arguing about who is the toppest and leftist. So Siggy Sigwald says, I should organize a trip to Tierra del Fuego and stream 24 hours on December 21st to put this thing to rest once and for all. Yeah, and December 21st. But it's not quite in the Antarctic Circle, is it? So it's not 24 hours. Of course, they just, everything's fake to them. The black box of they. You would be they. Faked it, of course. Yes. If I like this Tesla bit and radio free, if free energy was a thing, we would be using it for radio communications and use backup generators or batteries. Yeah. Every single free energy thing, the guy's like, I can, power my car on just water by sending electrolysis through it. Well, the battery ran out. I just got to tweak a few things, then I'll totally get it. And they never tweak those things because definitely they somehow were involved. No. PhD Tony's neutrino detector. I would, That would be good. That'd be good to have a to pull that. If you have any, not too many, don't overwhelm me, Tony, PT Tony. If you have a couple that specifically can identify direction, that would be good. Because the direction of a neutrino coming in there, you can't, there's no explanation on flat Earth other than to just hand wave deny that neutrinos exist. But, you know, neutrinos aren't affected by refraction or gravity. So, IC Spin says ChatGPT is a fair game. Okay, ask ChatGPT what shape the Earth is. And that's the thing. They love to just cherry pick. I will go to this source when it agrees with me, and I will no. They will then reject that same source when it disagrees with them. That's when the people that cherry pick the definition of level, they specifically find the definition of level that doesn't include the adjective referring to the shape of the Earth. And they're like, aha! But that's, you just cherry picked from that. Look up in that same dictionary, Earth. See what it says. Casey Cooper. Hey, Toon, are you McTyrant on Elvenar? I don't know what Elvenar is. Yeah. So no, I'm not. Siggy Sigwald says, so you have to be incapable of thinking in 3D to be a flat earther. Maybe we got it wrong, and it's like 4D beings trying to explain us their reality. Could be. Could be. And it does seem to be the case. Like 3D stuff just always baffles them. Right? Like the position of stars. Like nothing about the position of stars works for flat Earth. It's got to magically take a path for no good reason from where they say they are in the firmament to where you are, right? If the firmament is rotating around you, then when you look south from close to the edge, you'd see the stars moving laterally. No, that doesn't make sense at all. There's no magic that could possibly explain that even. Mark Rudolph, I'm sorry that Caleb only came on because Simon Dan wasn't available. Brenda says Elvin are from Rivendell. Yes, I know Elvin are from Rivendell. But Elvin, what was that? Elvin, somebody, yeah, scrolled off. I'm sorry. Am I mixed somebody from Elvenar? I don't know. Greg Kotz says this kid's papa is Witsit. He's very top left. And like, you know, it's frustrating. You look at his videos on TikTok, and it's the memes, it's the Flurf memes from 2015. Right? And he just says, you know, he's like, they're so trivial. So trivial. Like he's like the speed of what was it? The speed of sound in knots. Yeah, the speed of sound in knots at sea level. He has a quote claiming it's 666 knots, but it's not. It's 666.7 knots. Or if you round to before the decimal point, it's 667 knots. In no case is it reasonably 666. It never is. Like, look it up. He didn't look up any of those things. It's trivial. Please. PT Tony, Barnard Star, perfect example of proper motion. Again, PhD Tony. Okay. Cepheid variable stars have a fixed brightness as a function of their period of variation. So observing their period tells us how bright they should be. Yes. Okay. And obviously I'm not super well backed on astronomy. And I do know Cepheid stars. I knew that because I had the astronomer on, and I read up on it because Blair's is a Cepheid star, I think. Man, see, I'm not up on it. Anyway, he talked about it. He went over that, so I had brushed up a bit on it. So yeah, they vary in their brightness. And that's how we know how bright they are and how much light we are receiving. Use inverse square law. So Tim Pryor says, it's like deja vu. If he would have watched the debate before this, we would not have asked the same dumb questions. Yeah, he only watched some of it. Siggy Sigwald says, we're not mean. It's because I was saying you're all mean. It's just hard not to laugh at Flurps. I still can't cope with the fact adult people don't understand this very basic thing. Yes. So how do you do? I mean, there are times when especially on Facebook, some of these people are so dumb. Just like, what the crap is going on in your tiny little walnut brain? But when I talk to somebody, I'm like, all right, I'm going to treat them nice. So when some of you like write stuff, it's easy from behind the keyboard to write something different than you would say to somebody. So when you write something and it's mean, I'm like, sometimes, you see it. Sometimes I editorialize it. I don't like being mean unless they really, really deserve it. And they really, really deserve it. 301 is coleslaw salad. Janusz Takas, and I'm sorry I mispronounced that, for 512 huffs. I appreciate that is a power of 2. Says, look at the RZA charts. It's almost done. Oh my goodness. So last week was it just Tuesday? It's just Tuesday, wasn't it? I don't know. I asked for volunteers. I think it was last week. Never. Anyway, to wanted to do some data entry, and a bunch of people did. I got 4 or 5 people that are like, yeah, I'd love to do data entry. So all of the zenith angles that are in the transcontinental triangulation, the American arc of the parallel survey are what are to be entered in. And so they've got almost all of them in. It's cool. And then, so that's really the tedious part, because I entered a few and I'm like, I'll never get this done. They came in and so thank you. You did a great job. And so when I get the details out, I'll call them out specifically for help. And it's been super helpful. And then the next phase is to pair them up. So here's what they did. They had from one location, they measured, the zenith angle. Let me get it over here. There we go. And from another to another location, right? So you've got this angle here, and it's a little more than 90. Already tells you something. And then from over here, they did the same thing to that same position, right? So 2 different positions measuring to each other. That's why it says reciprocal. And if the Earth were flat, they would sum to 180. Actually, because of refraction, they would sum to be slightly less than 180. But flat earthers don't even think refraction exists on flat Earth somehow. But in reality, if the Earth were actually flat, refraction would cause it to be slightly less than 180. And if the Earth is a globe, it will be more than 180. Well, anyway, so you take these measurements and we find the pair. So like, well, from Mount Como to to Para as an example. It's these 2 directions. So then we need to have another row, and this is where it can get tedious. We have to pair these up. Somewhere in this table, there's the one direction. Somewhere else in the table is the other direction. We need to bring them together. So that's where the actual software development happens. And I've got somebody emailed me today. I haven't read the email yet, but I did see the overview. Somebody has said he's a programmer, so I might have somebody that's in on. Also, Round Thinker from Israel was having a look. So I think we'll get that in, and then we'll have hundreds of reciprocal zenith angle measurements. I'll put it on screen. Okay, I will. I'll put it on screen. It is that cool. So, and actually, you all can see the work in progress. You all can. And how can you? Well, if you see what I'm about to show you, you will know exactly how. I won't tell you specifically, but you will know how. If you don't know how after watching this, how you can see their work in progress, then there's no help. There's no hope for you. I just showed you. So, all right. Here is my spherical excess calculations. This is opening up to page 1 or sheet 1. But look over here. We've got our ZAs right there. And there's a lot of data. It's loading up. So, look at that. That is awesome. So, yep, you're seeing them all. So you see, here is Pikes Peak East to Monte Rosa. And here is, oh my goodness, he even, oh, so nice. Here is the observed zenith in decimal degrees. So there's actually that they're in the book. They're as decimal, or sorry, as degrees, minutes, seconds. And so then I calculate out the decimal degrees here, 93. Holy crap, that's a wow, 97. That's a zenith. Wow. Anyway, maybe Monte Rosa is at low elevation. That would make sense then. Anyway, so then, all right, what am I? This is a little different than I left it last time. Okay, here we have some of the data that I entered. Mount Como, I mentioned. Mount Diablo, Mocha. Look at these. They just go and they go. And there it is. Round Top. There we go. I mentioned Mount Como. So here's Mount Como to Para. See that? And then right below it is Para to Mount Como. So that's the other direction. So if we look here, the first direction is 90 degrees, 0.499. So about 90.5 degrees. And then the other direction from Para to Mount Como is 90.185. So together, it's going to be 180.68 something. You subtract from 180 to get actually the angle between them at the core of the Earth, the center of the Earth, and it's 0.68 degrees. A significant amount, right? Because these are precise to 1 arc second, so 1/3600th. So many, and look at these pages. Look at this. So much, people. All this and data entry, so much. Thank you very much for that. Anyway, then here's this next page here where I actually do the summing, and I have just one in so far. Oh, it got moved, so it broke. So anyway, I had Mount Como and Para, but when they moved it, the reference broke. So I'll have to fix that. But the point is, this will be shortly, hopefully done, and we'll have all of those zenith measurements in there. So, yes, complete desolation for flat Earth. Impossible on flat Earth. Not even any remote possibility of an explanation. Nothing. And it doesn't work for concave. It destroys concave too. Those goofballs. Layouts a Discord channel. Yep, I will have to read that. So if you're on my Discord server, there's a Gotta Light a Flurf channel, and there's a Museum of Derp. The Museum of Derp is a protected channel because people kept having conversations in there, but it's meant to be a museum, so I had to lock it down so administrators and moderators can post in there. Leslie Rower says, remember that surface charge means a charge on the crust of less than 1 electron per trillion square meters. The charge on the crust of less than 1 electron per trillion square meters. So yeah, that would be a negative charge, not a zero charge, but okay. Random truth. Is random truth a flurf? Truth is in the name. 99% chance. Let's hear what random truth is. You guys ever looked at yourself like we did? YouTube has hid them all, but they can be found. Hey, random truth, it doesn't matter. I'll give you a non-random truth. Reciprocal zenith angles don't work on flat Earth. And the people doing data entry have There's hundreds of them. Hundreds of empirical measurements. You got nothing. Yeah, go look at yourselves. You've been fooled, random truth. You've been fooled. And I will have to add you to my truth YouTube channel of Truth Paradox. I got a couple member super chats. Pat in the chat says, Caleb, thoughts on Cavendish in a vacuum? And we did talk about that. And he didn't have much on that. All right, let me see here. We got Kirk B, who's been a member for 18 months, says, you cause McCladdy for versus TFE for charity. Oh, my cousin McFlatty versus TFE for versus FTFE. You think my cousin? Of course, my cousin McFlatty constantly challenges everybody, but he always runs away. But I maybe for charity he would. I don't know if the charity was to get him more Hot Pockets and Go-Gurts. He does like his Hot Pockets. All right. That is the remainder of the super chats. So Eric Erpelding says, when will Whitsitt give his debunk of spherical excess? He won't. So if you're wondering what is spherical excess, if you draw straight lines on the surface of a sphere, maybe get yourself an exercise ball and pull a string across it nice and tight, and then draw a line on that string. Or you could just tape the string to it. Do 3 lines like that. They will intersect. Then measure the angles between each of those lines. Now, a straight line on the surface of a sphere is curved along the surface, but when you look at it from straight above, it's straight. So the definition of straight line on the surface of a sphere is that it follows the curve of the sphere. That's the definition. So those angles, when you measure those angles and then sum them on the surface of a sphere, it will be greater than 180 and less than 540. At 540, you actually just have 3 lines that have now joined and overlapped perfectly. So, yeah, Mary Ann the Night Owl says, Seek Truth, Speak Truth is another one that isn't a flurf. I mean, he used to be, but the YouTube debunking family helped him out of the rabbit hole. Yes. And Craig is a friend of mine. I talk to him every once in a while. He has a great history channel. I forget the name. If somebody could remember, then find his history channel, put in the description here. It's super good. I love it. I can listen to somebody with a nice British accent talk about history all day long. It makes history listenable. And he's great at it. So anyway, it's the amount. So on a flat plane, a triangle has 180. On a sphere, it has more. The amount more than 180 is called spherical excess. Large surveys that have very large triangles in them are able to measure, to the precision of the measuring instrument, are able to measure spherical excess more than 180 degrees in these triangles. And so the survey, the Transcontinental Triangulation American Earth Parallel, has a bunch of them, and that's what this data entry was about. So there's hundreds of triangles in there, and they all sum to more than 180 degrees. He looked at it and saw the non-completed value, right? And so they do these adjustment and corrections to them because of that. There's a bunch of reasons. So when you're at high elevation, you're above the surface of the earth, it's slightly different. When you are measuring angles of a triangle and you have multiple triangles in a network, these points don't all meet at the exact same point because there's measurement error. And when you do that, then you need to do some adjustments for them. So after the adjustments for all of these errors, all of these triangles sum to greater than 180 degrees. He is convinced, and he said it very explicitly twice, that he claimed that the surveyors baked in the radius of the Earth. Like, they knew what they were doing and they intentionally faked it. They intentionally faked all of the angles that were measured to match, is what he's saying. Claiming that they all were... How could they do that? They didn't have computers. This was published in 1901, so they would have had to spend years figuring out the necessary angles for these things. The amount of work he's suggesting is outrageous, but also what it would do is it would make the survey completely wrong. Yet the survey is not completely wrong. So there's a whole lot of problems with it. Anyway, he said that he's going to get to the bottom of it. He's going to find where they baked in the radius. Good luck on that, Austin. Doug's in Boston says, if random truth can't grasp a lot is 2 words, a space lot, no wonder he can't grasp Earth is a globe. Doug's in Boston. I'm all done being nice to them. All done. So, Rob Glow says, I had top secret security clearance in the Air Force, and I'm a flat earther. So here's the interesting thing. What you just did is called an appeal to authority, with yourself as the authority. Is your position in the Air Force, did it give you knowledge about the shape of the Earth? Could you share that? Or are you just saying, you know the Earth is flat, and because you were in the military, people should definitely believe you? Sorry, that doesn't help. If you had any special evidence, then you would just share it, right? So, much love, everybody, no matter what you believe. But here's the thing. Lying, I don't like lying, and so all this much love crap when somebody's lying, it's not all that interesting. So, oh yes, Baux says, I do astrophotography, and I have been told that the planetary and nebulae image are pre-programmed into my equipment. An amazing thing to be able to do, to somehow have that instrument know what direction you're looking, and also somehow know whether or not there's cloud cover. To somehow have pre-programmed it in to know that the Starlink satellites were orbiting. And so if you bought a telescope in the 1980s, how did they pre-program that Starlink was going to be launched and know where it was going to be so that it could ruin your photograph? They couldn't. So they couldn't. Hey, Astrorex is here. I haven't seen him for a while. So, all right. I am, I'll add, here we go. So people, thank you very much for this off schedule thing. I'll tell you a couple things. I was trying to get a video out for tomorrow. It's not going to happen. On Mikey Smith. Next week, I'm going to be on a podcast. That's a pretty good sized one. It's not a debate. It's a response to a flat earther having been on that podcast, and it's not dearth. So, Tuesday, I have 2 things on Tuesday. I will be on somebody else's channel at 6 p.m. Central. That's Christopher Enoch. I've been on there before. He's, if he might not be your style, he's a heavy religious guy. He and I don't see eye to eye on our particular spots on religion. But when it comes to the shape of the Earth, we're in agreement. So I'm there. And then after that, I have Brian Stavely, and he's going to talk about the Mandela effect. So, I don't know. I think it's derpy, and it's definitely not CERN that's doing it. But it's funny when they say that. So anyway, Brian and I think we'll have a good chat. So that's what's going on. Professor Egghead, McCartoon says he doesn't like to lie. What a liar! Oh, come on. You're being a little mean to me. Come on. I'm not kidding. You get a thick skin. So I prepped the video. I've had trouble with the outro video actually being loaded when I switch over to it. We'll see. we'll see. Yeah, it's not. So yeah, his name is Christopher Enoch. He doesn't nothing about the Book of Enoch, which I don't think he thinks is anything all that useful. The Book of Enoch is go read it. I listened to it on there's a YouTube video that just has all of it read. I listened to it while mowing the lawn. So anyway, there it is. Hopefully the video won't freeze. We'll see. But everybody, thank you very much to members, super chatters, Siggy Sigwald for gifting those memberships. We'll see you next time. Hey, the outro worked. Awesome. All right, people, see you.